Okay. So, welcome. Practical Deep Learning for Coders, Lesson 1. It's kind of Lesson 2 because there's a Lesson 0, and Lesson 0 is why do you need a GPU and how do you get it set up. So if you haven't got a GPU running yet, then go back and do that. Make sure that you can access a Jupyter notebook and then you're ready to start the real Lesson 1. So if you're ready, you will be able to see something like this. In particular, hopefully you have gone to Notebook Tutorial. It's at the top. That's why I put a 00 here. As this grows, you'll see more and more files, but we'll keep Notebook Tutorial at the top. And you will have used your Jupyter notebook to add 1 and 1 together, getting the expected result. Let's make that a bit bigger. And hopefully you've learnt these 4 keyboard shortcuts. So the basic idea is that your Jupyter notebook has prose in it. It can have pictures in it. It can have charts in it. And most importantly, it can have code in it. Okay. So the code is in Python. How many people have used Python before? So nearly all of you. That's great. If you haven't used Python, that's totally okay. Right? It's a pretty easy language to pick up. But if you haven't used Python, this will feel a little bit more intimidating because the code that you're seeing will be unfamiliar to you. Yes, Rachel?
I was going to say, for people in the room, it's okay if they don't have the code, right?
Oh, yeah. No, because I'm trying to keep them both separate.
Sorry.
Yeah. Okay, well, now that we're here, I'll edit this bit out. So, as I say, there are things like this where people in the room, in person, this is one of those bits where it's like this is really for the MOOC audience, not for you. I think this will be the only time like this in the lesson where we've assumed you've got this set up. Thanks for the reminder. Okay. All right. So yeah, for those of you in the room or on FastAI Live, you can go back after this and make sure that you can get this running using the information in course v3.fastai. Okay. Great. Okay, so a Jupyter notebook is a really interesting device for a data scientist because it kind of lets you run interactive experiments and it lets us give you not just a static piece of information, but it lets us give you something that you can actually interactively experiment with. So let me explain how we think works well to use these notebooks and to use this material. And this is based on the kind of last 3 years of experience we've had with the students who have gone through this course. First of all, it works pretty well just to watch a lesson end to end. Right? Don't try and follow along because it's not really designed to go at a speed where you can follow along. It's designed to be something where you just take in the information, you get a general sense of all of the pieces, how it all fits together. Right? And then you can go back and go through it more slowly, pausing in the video and trying things out, making sure that you can do the things that I'm doing, and that you can try and extend them to do things in your own way. Okay? So don't worry if things are zipping along faster than you can do them. That's normal. Also, don't try and stop and understand everything the first time. If you do understand everything the first time, good for you. But most people don't, particularly as the lessons go on. They get faster and they get more difficult. Okay. So at this point, we've got our notebooks going. We're ready to start doing deep learning. And so the main thing that hopefully you're going to agree at the end of this is that you can do deep learning, regardless of who you are. And we don't just mean do, we mean do at a very high level. We mean world-class practitioner level deep learning. Okay. So your main place to be looking for things is course v3.fast.ai. where you can find out how to get a GPU, other information, and you can also access our forums. You can also access our forums, and on our forums you'll find things like how do you build a deep learning box yourself, and that's something that you can do after, later on once you've kind of got going. Who am I? So why should you listen to me? Well, maybe you shouldn't, but I'll try and justify why you should listen to me. I've been doing stuff with machine learning for over 25 years. I started out in management consulting, where actually initially I was, I think, McKinsey and Company's first analytical specialist, and went into general consulting. Ran a number of startups for a long time. Eventually became the president of Kaggle. But actually the thing I'm probably most proud of in my life is that I got to be the #1 ranked contestant in Kaggle competitions globally. So I think that's a good kind of practical, like, can you actually train a predictive model that predicts things? Pretty important aspect of data science. I then founded a company called Analytic, which was the first kind of medical deep learning company. Nowadays, I'm on the faculty at University of San Francisco and also co-founder with Rachel of FastAI. So I've used machine learning throughout that time, and I guess I'm not really, although I am at USF at a university, I'm not really an academic type. I'm much more interested in using this tool to do useful things. Specifically, through FastAI, we are trying to help people use deep learning to do useful things through creating software to make deep learning easier to use at a very high level, through education, such as the thing you're watching now, through research, which is where we spend a very large amount of our time, which is researching to figure out how can you make deep learning easier to use at a very high level, which ends up in, as you'll see, in the software and the education, and by helping to build a community, which is mainly through the forums, so that practitioners can find each other and work together. So that's what we're doing. So this lesson, Practical Deep Learning for Coders, is kind of the starting point in this journey. It contains 7 lessons, each one's about 2 hours long. We're then expecting you to do about 8 to 10 hours of homework during the week. So it'll end up being something around 70 or 80 hours of work. I will say it varies a lot as to how much people put into this. I know a lot of people who work full-time on FastAI. Some folks who do the 2 parts can spend a whole year doing it really intensively. I know some folks watch the videos on double speed and never do any homework and come out the end of it with, a general sense of what's going on. So there's lots of different ways you can do this. But if you follow along with this kind of 10 hours a week or so approach for the 7 weeks, by the end, you will be able to build an image classification model on pictures that you choose that will work at a world-class level. You'll be able to classify text, again, using whatever data sets you're interested in. You'll be able to make predictions of kind of commercial applications like sales. You'll be able to build recommendation systems, such as the one used by Netflix. Not toy examples of any of these, but actually things that can come top 10 in Kaggle competitions, that can beat everything that's in the academic community, very, very high-level versions of these things. So that might surprise you, that the prerequisite here is literally 1 year of coding and high school math, but we have thousands of students now who have done this and shown it to be true. You will probably hear a lot of naysayers, less now than a couple of years ago than we started, but a lot of naysayers telling you that you can't do it, or that you shouldn't be doing it, or that deep learning's got all these problems. It's not perfect, but these are all things that people claim about deep learning, which are either pointless or untrue. It's not a black box. As you'll see, it's really great for interpreting what's going on. It does not need much data for most practical applications. You certainly don't need a PhD. Rachel has one, so it doesn't actually stop you from doing deep learning if you have a PhD. I certainly don't. I have a philosophy degree and nothing else. It can be used very widely for lots of different applications, not just for vision, which is where it's most well known. You don't need lots of hardware. You know, that 36 cent an hour server is more than enough to get world-class results for most problems. It's true that maybe this is not going to help you to build a sentient brain, but that's not our focus. Okay, so for all the people who say deep learning is not interesting because it's not really AI, not really a conversation that I'm interested in. We're focused on solving interesting real-world problems. What are you going to be able to do by the end of lesson 1? Well, this was an example from Nikhil, who's actually in the audience now because he was in last year's course as well. This is an example of something he did, which is he downloaded 30 images of people playing cricket and people playing baseball and ran the code you'll see today and built a nearly perfect classifier of which is which. So it's kind of stuff that you can build with some fun hobby examples like this, or you can try stuff, as we'll see, in the workplace that could be of direct commercial value. So this is the idea of where we're going to get to by the end of lesson 1. We're going to start by looking at code, which is very different to many of the academic courses. So for those of you who have a kind of an engineering or math or computer science background, this is very different to the approach where you start with lots and lots of theory, and then eventually you get to a postgraduate degree and you finally are at the point where you can build something useful. We're going to learn to build the useful thing today. Okay. Now that means that at the end of today, you won't know all the theory. Okay. There will be lots of aspects of what we do that you don't know why or how it works. That's okay. You will learn why and how it works over the next 7 weeks. But for now, we've found that what works really well is to actually get your hands dirty coding, not focusing on theory. Because there's still a lot of artisanship in deep learning, unfortunately. It's still a situation where people who are good practitioners have a really good feel for how to work with the code and how to work with the data. And you can only get that through experience. And so the best way to get that feel of how to get good models is to create lots of models, do lots of coding, and study them carefully. And Jupyter Notebook provides a really great way to study them. So let's try that. Let's try getting started. So to get started, you will open your Jupyter Notebook, and you'll click on Lesson 1. Lesson 1, Pets. And it will pop open looking something like this. And so here it is. So you can run a cell in a Jupyter Notebook by clicking on it and pressing Run. But if you do so, everybody will know that you're not a real deep learning practitioner, because real deep learning practitioners know the keyboard shortcuts. And the keyboard shortcut is Shift-Enter. Given how often you have to run a cell, don't be going all the way up here, finding it, clicking it, just Shift-Enter, okay? So type, Shift-Enter, type, Shift-Enter. Up and down to move around, to pick something to run, Shift-Enter to run it, okay? So we're going to go through this quickly, and then later on we're going to go back over it more carefully. So here's the quick version to get a sense of what's going on. So here we are in Lesson 1, and these 3 lines is what we start every notebook with. These things starting with % are special directives to Jupyter Notebook itself. They're not Python code. They're called magics, which is kind of a cool name. And these 3 directives, the details aren't very important, but basically it says, hey, if somebody changes the underlying library code while I'm running this, please reload it automatically. If somebody asks to plot something, then please plot it here in this Jupyter Notebook. So just put those 3 lines at the top of everything. The next 2 lines load up the FastAI library. What is the FastAI library? So it's a little bit confusing. FastAI with no dot is the name of our software, and then fast.ai with the dot is the name of our organization. So if you go to docs.fast.ai, this is the FastAI library. Okay, we'll learn more about it in a moment, but for now, just realize everything we are going to do is going to be using basically either FastAI or the thing that FastAI sits on top of, which is PyTorch. PyTorch is one of the most popular libraries for deep learning in the world. It's a bit newer than TensorFlow, so in a lot of ways it's more modern than TensorFlow. It's extremely fast-growing, extremely popular, and we use it because, well, we used to use TensorFlow a couple of years ago, and we found we can just do a lot more quickly with PyTorch. And then we have this software that sits on top of PyTorch and lets you do far more things, far more easily than you can with PyTorch alone. So it's a good combination. We'll be talking a lot about it. But for now, just know that you can use FastAI by doing two things. Importing star from FastAI, and then importing star from fastai.something, where something is the application you want. And currently FastAI supports 4 applications: computer vision, natural language text, tabular data, and collaborative filtering. Okay, and we're going to see lots of examples of all of those during the 7 weeks. So we're going to be doing some computer vision. At this point, if you are a Python software engineer, you are probably feeling sick because you've seen me go import star, which is something that you've all been told to never ever do. Okay, and there's very good reasons to not use import star in standard production code with most libraries. But you might have also seen, for those of you that have used something like MATLAB, it's kind of the opposite. Everything's there for you all the time. You don't even have to import things a lot of the time. It's kind of funny. We've got these two extremes of like, how do I code? You've got the scientific programming community that has one way, and then you've got the software engineering community that has the other. Both have really good reasons for doing things, and with the FastAI library, we actually support both approaches. In a Jupyter notebook, where you want to be able to quickly, interactively try stuff out, you don't want to be constantly going back up to the top and importing more stuff and trying to figure out where things are. You want to be able to use lots of tab complete, be very experimental, so import star is great. Then when you're building stuff in production, you can do the normal PEP 8 style, proper software engineering practices. So don't worry when you see me doing stuff which at your workplace is frowned upon. Okay, this is a different style of coding. It's not that there are no rules in data science programming, it's that the rules are different, right? When you're training models, the most important thing is to be able to interactively experiment quickly. Okay, so you'll see we use a lot of very different processes, styles, and stuff to what you're used to, but they're there for a reason, and you'll learn about them over time. You can choose to use a similar approach or not. It's entirely up to you. The other thing to mention is that the FastAI libraries designed in a very interesting modular way, and you'll find over time that when you do use import star, there's far less clobbering of things than you might expect. It's all explicitly designed to allow you to pull in things and use them quickly without having problems. Okay, so we're going to look at some data. And there's 2 main places that we'll be tending to get data from for the course. One is from academic data sets. Academic data sets are really important, they're really interesting. They're things where academics spend a lot of time curating and gathering a data set so that they can show how well different kinds of approaches work with that data. And the idea is they try to design data sets that are challenging in some way and require some kind of breakthrough to do them well. So we're going to be starting with an academic data set called the PET data set. The other kind of data set we'll be using during the course is data sets from the Kaggle competitions platform. Both academic data sets and Kaggle data sets are interesting for us, particularly because they provide strong baselines. That is to say, you want to know if you're doing a good job. So with Kaggle data sets that have come from a competition, you can actually submit your results to Kaggle and see how well would you have gone in that competition. And if you can get in about the top 10%, then I'd say you're doing pretty well. For academic data sets, academics write down in papers what the state of the art is. So how well did they go with using models on that data set? Okay. So this is what we're going to do. We're going to try and create models that get right up towards the top of Kaggle competitions, preferably actually in the top 10, not just the top 10%, or that meet or exceed academic state-of-the-art published results. When you use an academic data set, it's important to cite it. So you'll see here there's a link to the paper that it's from. You definitely don't need to read that paper right now, but if you're interested in learning more about it and why it was created and how it was created, all the details are there. So in this case, this is a pretty difficult challenge. The pet data set is going to ask us to distinguish between 37 different categories of dog breed and cat breed. So that's really hard. In fact, every course until this one, we've used a different data set, which is one where you just have to decide is something a dog or is it a cat. So you've got a 50-50 chance right away, right? And dogs and cats look really different, whereas lots of dog breeds and cat breeds look pretty much the same. So why have we changed our data set? We've got to the point now where deep learning is so fast and so easy that the dogs versus cats problem, which a few years ago was considered extremely difficult, 80% accuracy was the state of the art, it's now too easy. Our models were basically getting everything right all the time without any tuning, and so there weren't really a lot of opportunities for me to show you how to do more sophisticated stuff. So we've picked a harder problem this year. So this is the first class where we're going to be learning how to do this difficult problem. And this kind of thing where you have to distinguish between similar categories is called, in the academic context, it's called fine-grained classification. So we're going to do the fine-grained classification task of figuring out a particular kind of pet. And so the first thing we have to do is download and extract the data that we want. We're going to be using this function called untar data, which will download it automatically and will untar it automatically. AWS has been kind enough to give us lots of space and bandwidth for these data sets, so they'll download super quickly for you. And so the first question then would be, how do I know what untar data does? So you can just type help, and you will find out what module did it come from, because since we imported star, we don't necessarily know that. What does it do? And something you might not have seen before, even if you're an experienced programmer, is what exactly do you pass to it? You're probably used to seeing the names, URL, file name, destination, but you might not be used to seeing these bits. These bits are types. Okay, and if you've used a type programming language, you'll be used to seeing them, but Python programmers are less used to it. But if you think about it, you don't actually know how to use a function unless you know what type each thing is that you're providing it. So we make sure that we give you that type information directly here in the help. So in this case, the URL is a string, and the file name is either, union means either a path or a string, and it defaults to nothing. And the destination is either a path or a string, and it defaults to nothing. So we'll learn more shortly about how to get more documentation about the details of this. But for now, we can see we don't have to pass in a file name or a destination. It'll figure them out for us from the URL. So, and for all the data sets we'll be using in the course, we already have constants defined for all of them, right? So in this URLs module, or class actually, you can see that's where it's going to grab it from. Okay, so it's going to download that to some convenient path and untar it for us, and will then return the value of path. Okay, and then in Jupyter Notebook, it's kind of handy. You can just write a variable on its own, right? And semicolon is just an end of statement marker in Python, so it's the same as doing this. You can write it on its own, and it prints it. You can also say print, right? But again, we're trying to do everything fast and interactively. Just write it, and here is the path where it's given us our data. Next time you run this, since you've already downloaded it, it won't download it again. Since you've already untarred it, it won't untar it again. So everything's kind of designed to be pretty automatic, pretty easy. There are some things in Python that are less convenient for interactive use than they should be. For example, when you do have a path object, seeing what's in it actually takes a lot more typing than I would like. So sometimes we add functionality into existing Python stuff. One of the things we do is we add an ls method to paths. So if you go path.ls, here is what's inside this path. So that's what we just downloaded. So when you try this yourself, you wait a couple of minutes for it to download, unzip, and then you can see what's in there. If you're an experienced Python programmer, you may not be familiar with this approach of using a slash like this. This is a really convenient function that's part of Python 3. It's functionality from something called pathlib. These are path objects. Path objects are much better to use than strings. That lets you basically create subpaths like this Doesn't matter if you're on Windows, Linux, Mac, it's always going to work exactly the same way. So here's a path to the images in that data set. All right, so if you're starting with a brand new data set, trying to do some deep learning on it, what do? Well, the first thing you would want to do is probably see what's in there. So we found that these are the directories that are in there. So what's in this? Images. There's a lot of functions in FastAI for you. There's one called getImageFiles that will just grab an array of all of the image files based on extension in a path. And so here you can see we've got lots of different files. Okay, so this is a pretty common way for computer vision data sets to get passed around, is that there's just one folder with a whole bunch of files in. So the interesting bit then is, how do we get the labels? So in machine learning, the labels refer to the thing we're trying to predict. And if we just eyeball this, we can immediately see that the labels are actually part of the file name. You see that, right? It's kind of like path/label_number extension. So we need to somehow get a list of these bits of each file name, and that will give us our labels. Because that's all you need to build a deep learning model. You need some pictures, so files containing the images, and you need some labels. So in FastAI, this is made really easy. There's a object called image data bunch, and an image data bunch represents all of the data you need to build a model. And there's basically some factory methods which try to make it really easy for you to create that data bunch. We'll talk more about this shortly, but a training set and a validation set with images and labels for you. Now in this case, we can see we need to extract the labels from the names. Okay, so we're going to use from name RE. So for those of you that use Python, you'll know RE is the module in Python that does regular expressions, things that's really useful for extracting text. I just went ahead and created the regular expression that would extract the label from this text. Okay, so those of you who are not familiar with regular expressions, super useful tool. It'd be very useful to spend some time figuring out how and why that particular regular expression is going to extract the label from this text. Okay. So with this factory method, we can basically say, okay, I've got this path containing images. This is a list of file names. Remember, I got them back here. This is the regular expression pattern that is going to be used to extract the label from the file name. We'll talk about transforms later. And then you also need to say, what size images do you want to work with? So that might seem weird. Why do I need to say what size images I want to work with? Because the images have a size. We can see what size the images are. And I guess, honestly, this is a shortcoming of current deep learning technology, which is that a GPU has to apply the exact same instruction to a whole bunch of things at the same time in order to be fast. And so if the images are different shapes and sizes, it can't do that. Right? So we actually have to make all of the images the same shape and size. In part one of the course, we're always going to be making images square shapes. In part two, we'll learn how to use rectangles as well. It turns out to be surprisingly nuanced. Right? But pretty much everybody in pretty much all computer vision modeling, nearly all of it, uses this approach of square. And 224 by 224, for reasons we'll learn about, is an extremely common size that most models tend to use. So if you just use size equals 224, you're probably going to get pretty good results most of the time. And this is kind of the little bits of artisanship that I want to teach you folks, which is like what generally just works. Okay, so if you just use size equals 224, that'll generally just work for most things most of the time. So this is going to return a data bunch object. And in FastAI, everything you model with is going to be a data bunch object. We're going to learn all about them and what's in them and how do we look at them and so forth. But basically, a data bunch object contains 2 or 3 data sets. It contains your training data. We'll learn about this shortly. It'll contain your validation data, and optionally it contains your test data. And for each of those, it contains your your images and your labels, or your texts and your labels, or your tabular data and your labels, or so forth. And that all sits there in this one place. Something we'll learn more about a little bit is normalization, but generally in nearly all machine learning tasks, you have to make all of your data about the same size, specifically about the same mean and about the same standard deviation. So there's a normalize function that we can use to normalize our data bunch in that way.
Getting a question.
Okay, Rachel, come and ask the question. Come over here. Thanks.
What does the function do if the image size is not 224?
Great. So this is what we're going to learn about shortly. Basically, this thing called transforms is used to do a number of things, and one of the things it does is to make something size 224. Let's take a look at a few pictures. Here are a few pictures of things from my data bunch. So you can see data.showBatch can be used to show me the contents of some of the contents in my data bunch. So this is going to be 3 by 3. And you can see roughly what's happened is that they all seem to have been kind of zoomed and cropped in a reasonably nice way. So basically what it'll do is something called, by default, center cropping, which means it'll kind of grab the middle bit and it'll also resize it. So we'll talk more about the details of this because it turns out to actually be quite important. But basically a combination of cropping and resizing is used. Something else we'll learn about is we also use this to do something called data augmentation. So there's actually some randomization in how much and where it crops and stuff like that. Okay, but that's the basic idea, is some cropping and some resizing. Often we also do some padding. So there's all kinds of different ways, and it depends on data augmentation, which we're going to learn about shortly.
And what does it mean to normalize the images?
So normalizing the images we're going to be learning more about later in the course, but in short it means that the pixel values, and we're going to be learning more about pixel values, the pixel values start out from 0 to 255, and some pixel values might tend to be really, well, I should say some channels, because there's red, green, and blue. So some channels might tend to be really bright, and some might tend to be really not bright at all, and some might vary a lot, and some might not vary much at all. It really helps train a deep learning model if each one of those red, green, and blue channels has a mean of 0 and a standard deviation of 1. Okay? We'll learn more about that. If you haven't studied or don't remember means and standard deviations, we'll get back to some of that later. But that's the basic idea. That's what normalization does. If your data, and again, we'll learn much more about the details, but if your data is not normalized, it can be quite difficult for your model to train well. So if you do have trouble training a model, one thing to check is that you've normalized it.
As GPU mem will be in power of 2, doesn't size 256 sound more practical, considering GPU utilization?
So we're going to be getting into that shortly, but the brief answer is that the models are designed so that the final layer is of size 7 by 7. So we actually want something where if you go 7 times 2 a bunch of times, then you end up with something that's a good size. Yeah, all of these details we are gonna get to. But the key thing is I wanted to get you training a model as quickly as possible. But you know, one of the most important things to be a really good practitioner is to be able to look at your data. Okay, so it's really important to remember to go data.showBatch and take a look. It's surprising how often when you actually look at the data set you've been given that you realize it's got weird black borders on it, or some of the things have text covering up some of it, or some of it's rotated in odd ways. So make sure you take a look. Okay. And then the other thing we want to do is not just look at the pictures, but also look at the labels. And so all of the possible label names are called your classes. Right? So in the data bunch, you can print out your data.classes. And so here they are. That's all of the possible labels that we found by using that regular expression on the file names. And we learned earlier on in that prose I wrote at the top that there are 37 possible categories. And so just checking length, data.classes, it is indeed 37. A data bunch will always have a property called C. And that property called C, the technical details will kind of get to later, but for now you can kind of think of it as being the number of classes. For things like regression problems and multi-label classification and stuff, that's not exactly accurate, but it'll do for now. It's important to know that data.c is a really important piece of information that is something like, or at least for classification problems, it is the number of classes. All right, believe it or not, we're now ready to train a model. And so a model is trained in FastAI using something called a learner. And just like a data bunch is a general FastAI concept for your data, and from there are subclasses for particular applications, like image data bunch. A learner is a general concept for things that can learn to fit a model, and from that there are various subclasses to make things easier. And in particular, there's one called conv learner, which is something that will create a convolutional neural network for you. And we'll be learning a lot about that over the next few lessons. But for now, just know that to create a learner for a convolutional neural network, you just have to tell it two things. The first is, what's your data? And not surprisingly, it takes a data bunch. And the second thing you need to tell it is, what's your model? Or what's your architecture? So as we'll learn, there are lots of different ways of constructing a convolutional neural network. But for now, the most important thing for you to know is that there's a particular kind of model called a Resnet, which works extremely well nearly all the time. And so for a while at least, you really only need to be choosing between two things, which is what size Resnet do you want? Okay, just basically, how big is it? And we'll learn all about the details of what that means. But there's one called a Resnet 34, and there's one called a Resnet 50. And so when we're getting started with something, I'll pick the smaller one because it'll train faster. So that's kind of it. That's as much as you need to know to be a pretty good practitioner about architectures for now, which is that there's two architectures, or two variants of one architecture that work pretty well, Resnet 34 and Resnet 50. Start with the smaller one and see if it's good enough. So that is all the information we need to create a convolutional neural network learner. There's one other thing I'm going to give it though, which is a list of metrics. Metrics are literally just things that get printed out as it's training. So I'm saying I would like you to print out the error rate, please. Now you can see the first time I ran this on a newly installed box, it downloaded something. What's it downloading? It's downloading the Resnet 34 pre-trained weights. Now what this means is that this particular model has actually already been trained for a particular task. And that particular task is that it was trained on looking at about 1.5 million pictures of all kinds of different things, 1,000 different categories of things, using an image, a data set called ImageNet. And so we can download those pre-trained weights so that we don't start with a model that knows nothing about anything, but we actually start with a model that knows how to recognize the 1,000 categories of things in ImageNet. Now, I'm not sure, but I don't think all of these 37 categories of pet were in ImageNet, but there were certainly some kinds of dog, and there were certainly some kinds of cat. So this pre-trained model already knows quite a little bit about what pets look like, and it certainly knows quite a lot about what animals look like and what photos look like. So the idea is that we don't start with a model that knows nothing at all, but we start by downloading a model that knows something about recognizing images already. So it downloads for us automatically the first time we use it, a pre-trained model. And then from now on, it won't need to download it again. It'll just use the one we've got. This is really important. We're going to learn a lot about this. It's kind of the focus of the whole course, which is how to do, this is called transfer learning. How to take a model that already knows how to do something pretty well and make it so that it can do your thing really well. We take a pre-trained model and then we fit it so that instead of predicting the 1,000 categories of ImageNet with the ImageNet data, it predicts the 37 categories of pets using your pet data. And it turns out that by doing this, you can train models in 1/100th or less of the time of regular model training with 1/100th or less of the data of regular model training. In fact, potentially many thousands of times less. Remember I showed you the slide of Nikhil's Lesson 1 project from last year? He used 30 images. And there's not cricket and baseball images in ImageNet, right? But it just turns out that ImageNet's already so good at recognizing things in the world that just 30 examples of people playing baseball and cricket was enough to build a nearly perfect classifier. Okay. Now, you would naturally be potentially saying, well, wait a minute, how do you know that it was going to that it can actually recognize pictures of people playing cricket versus baseball in general? Maybe it just learned to recognize those 30. Maybe it's just cheating, right? And that's called overfitting. We'll be talking a lot about that during this course, right? But overfitting is where you don't learn to recognize pictures of, say, cricket versus baseball, but just these particular cricketers and these particular photos and these particular baseball players and these particular photos. We have to make sure that we don't overfit. And so the way we do that is using something called a validation set. A validation set is a set of images that your model does not get to look at. And so these metrics, like in this case error rate, get printed out automatically using the validation set, a set of images that our model never got to see. When we created our data bunch, it automatically created a validation set for us. Okay? And we'll learn lots of ways of creating and using validation sets, but because we try to bake in all of the best practices, we actually make it nearly impossible for you not to use a validation set. Because if you're not using a validation set, you don't know if you're overfitting. Okay? So we always print out the metrics on a validation set, we always hold it out, we always make sure that the model doesn't touch it. That's all done for you. Okay? And that's all built into this data bunch object. So now that we have a conv learner, we can fit it. You can just use a method called fit, but in practice, you should nearly always use a method called fit one cycle. We'll learn more about this during the course, but in short, one cycle learning is a paper that was released, I'm trying to think, a few months ago, less than a year ago.
March?
Yeah, so a few months ago, and it turned out to be dramatically better, both more accurate and faster than any previous approach. So again, I don't want to teach you how to do 2017 deep learning. Right? In 2018, the best way to fit models is to use something called one cycle. We'll learn all about it, but for now, just know you should probably type learn.fit one cycle. Right? If you forget how to type it, you can start typing a few letters and hit tab, okay, and you'll get a list of potential options. Right? And then if you forget what to pass it, you can press Shift tab, and it'll show you exactly what to pass it. So you don't actually have to type help. And again, this is kind of nice that we have all the types here because we can see cycle length, we'll learn more about what that is shortly, is an integer, and then max learning rate could either be a float or a collection or whatever, and so forth. And you can see that momentums will default to this tuple, so on and so forth. Okay, so for now, just know that this number 4 basically decides how many times do we go through the entire data set? How many times do we show the data set to the model so that it can learn from it? Each time it sees a picture, it's going to get a little bit better, but it's going to take time, and it means it could overfit. If it sees the same picture too many times, it'll just learn to recognize that picture, not pets in general. We'll learn all about how to tune this number during the next couple of lessons, but starting out with 4 is a pretty good start, just to see how it goes. And you can actually see after 4 epochs, or 4 cycles, we've got an error rate of 6%. So a natural question is, how long did that take? That took 1 minute and 56 seconds. Yeah. So we're paying, 60 cents an hour. We just paid for 2 minutes of time. I mean, we actually pay for the whole time that it's on and running, but we use 2 minutes of compute time. And we got an error rate of 6%. So 94% of the time, we correctly picked the exact right one of those 94 dog and cat breeds, which feels pretty good to me. But to get a sense of how good it is, maybe we should go back and look at the paper. Just remember, I said the nice thing about using academic papers or Kaggle data sets is we can compare our solution to whatever the best people in Kaggle did or whatever the academics did. So this particular data set of pet breeds is from 2012. And if I scroll through the paper, you'll generally find in any academic paper there'll be a section called experiments about 2/3 of the way through. And if you find the section on experiments, then you can find the section on accuracy. And they've got lots of different models. And their models, as you'll read about in the paper, are extremely kind of pet specific. They learn something about how pet heads look and how pet bodies look and pet images in general look, and they combine them all together. And once they use all of this complex code and math, they got an accuracy of 59%. Okay, so in 2012, this highly pet-specific analysis got an accuracy of 59%. And these were the top researchers from Oxford University. Today, in 2018, with basically, if you go back and look at actually how much code we just wrote, it's about 3 lines of code. The other stuff is just printing out things to see what we're doing. We got 94%, so 6% error. So like that gives you a sense of, you know, how far we've come with deep learning, and particularly with PyTorch and FastAI, how easy things are. Yeah. So before we take a break, I just want to check to see if we've got any. And just remember, if you're in the audience and you see a question that you want asked, please click the love heart next to it so that Rachel knows that you want to hear about it. Also, if there is something with 6 likes and Rachel didn't notice it, which is quite possible, just quote it in a reply and say, hey, Rachel, this one's got 6 likes. Okay, so what we're going to do is we're going to take a 8-minute break. So we'll come back at 8:05. So where we got to was we just trained a model. We don't exactly know what that involved or how it happened, but we do know that with 3 or 4 lines of code, we built something which smashed the accuracy of the state-of-the-art of 2012. 6% error certainly sounds like pretty impressive for something that can recognize different dog breeds and cat breeds. But we don't really know why it works, but we will. That's okay. Right? And in terms of getting the most out of this course, we very, very regularly hear after the course is finished the same basic feedback, which this is literally copy and pasted from the forum. I fell into the habit of watching the lectures too much and Googling too much about concepts without running the code. At first I thought I should just read it and then research the theory. Okay? And we keep hearing people saying, my number one regret is I just spent 70 hours doing that. And at the very end, I started running the code, and oh, it turned out I learned a lot more. So please, run the code. Really run the code. I should have spent the majority of my time on the actual code in the notebooks, running it, seeing what goes in, and seeing what comes out. So your most important skills to practice are learning, and we're going to show you how to do this in a lot more detail, but understanding what goes in and what goes out. So we've already seen an example of looking at what goes in, which is data.showBatch. And that's going to show you examples of labels and images. And so next, we're going to be seeing how to look at what came out. Right? So that's the most important thing to study. As I said, the reason we've been able to do this so quickly is heavily because of the FastAI library. Now, the FastAI library is pretty new, but it's already getting an extraordinary amount of traction. As you've seen, all of the major cloud providers either support it or are about to support it. A lot of researchers are starting to use it. It's making a lot of things a lot easier, but it's also making new things possible. And so really understanding the FastAI software is something which is going to take you a long way. And the best way to really understand the FastAI software well is by using the FastAI documentation. And we'll be learning more about the FastAI documentation shortly. So how does it compare? I mean, there's really only one major other piece of software like FastAI that is something that tries to make deep learning easy to use. and that's Keras. Keras is a really terrific piece of software. We actually used it for the previous courses until we switched to FastAI. It runs on top of TensorFlow. It was kind of the gold standard for making deep learning easy to use before, but life is much easier with FastAI. So if you look, for example, at the last year's course exercise, which is getting dogs versus cats, FastAI lets you get much more accurate, less than half the error on a validation set, of course. Training time is less than half the time. Lines of code is about a sixth of the lines of code. And the lines of code are more important than you might realize, because those 31 lines of Keras code involve you making a lot of decisions, setting lots of parameters, doing lots of configuration. So that's all stuff where you have to know how to set those things to get kind of best practice results. Whereas these 5 lines of code, anytime we know what to do for you, we do it for you. Anytime we can pick a good default, we pick it for you. Okay? So hopefully you'll find this a really useful library, not just for learning deep learning, but for taking it a very long way. How far can you take it? Well, as you'll see, all of the research that we do at FastAI uses the library. And an example of the research we did, which was recently featured in Wired, describes a new breakthrough in natural language processing, which people are calling the ImageNet moment, which is basically we broke a new state-of-the-art result in text classification, which OpenAI then built on top of our paper to do with more compute and more data and some different tasks to take it even further. And this is an example of something that we've done in the last 6 months, in conjunction actually with my colleague Sebastian Ruder. An example of something that's being built in the FastAI library, and you're going to learn how to use this brand new model in 3 lessons' time. And you're actually going to get this exact result from this exact paper yourself. Another example, one of our alums, Hamel Hussain, who you'll come across on the forum plenty because he's a great guy, very active, built a new system for natural language semantic code search. You can find it on GitHub, where you can actually type in English sentences and find snippets of code that do the thing you ask for. And again, that's being built with the FastAI library using the techniques you'll be learning in the next 7 weeks.
In production.
In production, yeah. Well, it's. I think at this stage it's part of their experiments platform, so it's kind of pre-production, I guess. And so the best place to learn about these things and get involved in these things is on the forums, where as well as categories for each part of the course, there's also a general category for deep learning where people talk about research papers, applications, so on and so forth. So even although today we're kind of going to focus on a small number of lines of code to do a particular thing, which is image classification, and we're not learning much math or theory or whatever, over these 7 weeks, and then part 2, another 7 weeks, we're going to go deeper and deeper and deeper. And so where can that take you? I want to give you some examples. That there is Sarah Hooker. She did our first course a couple of years ago. Her background was economics. Didn't have a background in coding, math, computer science. I think she started learning to code 2 years before she took our course. She helped develop something she started a nonprofit called Delta Analytics. They helped build this amazing system where they attached old mobile phones to trees in the Kenyan rainforests and used it to listen for chainsaw noises, and then they used deep learning to figure out when there was a chainsaw being used, and then they had a system set up to alert rangers to go out and stop illegal deforestation in the rainforests. So that was something that she was doing while she was in the course as part of her kind of class projects. What's she doing now? She is now a Google Brain researcher, which I guess is one of the top, if not the top place to do deep learning. She's just been publishing some papers. Now she is going to Africa to set up Google Brain's first deep learning AI research center in Africa. Now I'll say, she worked her ass off. She really, really invested in this course, not just doing all of the assignments, but also going out and reading Ian Goodfellow's book and doing lots of other things, but it really shows where somebody who has no computer science or math background at all can be now one of the world's top deep learning researchers and doing very valuable work. Another example from our most recent course, Christine Payne, she is now at OpenAI. And you can find her post and actually listen to her music samples she actually built something to do automatically create chamber music compositions that you can play and you can listen to online. And so, again, it's her background, math and computer science. Actually, that's her there, classical pianist. Now, I will say she's not your average classical pianist. She's a classical pianist who also has a master's in medical research from Stanford and studied neuroscience and was a high-performance computing expert at D.E. Shaw and was valedictorian at Princeton. Anyway, she, very annoying person, good at everything she does. But, I think it's really cool to see how a kind of a domain expert, in this case the domain of playing piano, can go through the Fast AI course and come out the other end at, I guess OpenAI would be, of the three top research institutes, Google Brain or OpenAI would be two of them, probably along with DeepMind. And interestingly, actually, one of our other students, or I should say alumni of the course, recently interviewed her for a blog post series he's doing on top AI researchers. And she said one of the most important pieces of advice she got was from me. And she said the piece of advice was pick one project, do it really well, make it fantastic. Okay, so that was the piece of advice she found the most useful. And we're going to be talking a lot about you doing projects and making them fantastic during this course. Having said that, I don't really want you to go to AI or Google Brain. What I really want you to do is go back to your workplace or your passion project and apply these skills there, right? Let me give you an example. MIT released a deep learning course, and they highlighted in their announcement for this deep learning course this medical imaging example. And one of our students, Alex, who is a radiologist, said, you guys just showed a model overfitting. I can tell because I'm a radiologist, and this is not what this would look like on a chest film. This is what it should look like, and this, as a deep learning practitioner, this is how I know that this is what happened in your model. So Alex is combining his knowledge of radiology and his knowledge of deep learning to assess MIT's model from just two images very accurately, right? And so this is actually what I want most of you to be doing, is to take your domain expertise and combine it with the deep learning practical aspects that you'll learn in this course and bring them together like Alex is doing here. And so a lot of radiologists have actually gone through this course now and have built journal clubs and American Council of Radiology practice groups. There's a Data Science Institute at the ACR now and so forth, and Alex is one of the people who's providing kind of a lot of leadership in this area. I would love you to do the same kind of thing that Alex is doing, which is to really bring deep learning leadership into your industry, into your social impact project, whatever it is that you're trying to do. So another great example of this was Melissa Fabros, who was a English literature PhD. I think she studied like gendered language in English literature or something. And actually, Rachel in a previous job taught her to code, I think. And then she came into the Fast AI course, and she helped Kiva, a micro-lending social impact organization, to build a system that can recognize faces. Why is that necessary? Well, we're going to be talking a lot about this. But because most AI researchers are white men, most computer vision software can only recognize white male faces effectively. In fact, I think it was IBM's system is like 99.8% accurate on common white face men versus 60% accurate, 65% accurate on dark-skinned women. So it's like, what is that, like 30 or 40 times worse for black women versus white men. And this is really important because for Kiva, black women are, perhaps the most common user base for their micro-lending platform. So Melissa, after taking our course, and again, working her ass off and being super intense in her study and her work, won this $1 million AI challenge for her work for Kiva. Karthik did our course and realized that the thing he wanted to do wasn't at his company, it was something else, which is to help blind people to understand the world around them, so he started a new startup. You can find it now, it's called Envision. You can download the app, you can point your phone at things, and it will tell you what it sees. And I actually talked to a blind lady about these kinds of apps the other day, and she confirmed to me this is a super useful thing for visually disabled users. And it's the level that you can get to with the content that you're going to get over these 7 weeks and with this software can get you right to the cutting edge in areas you might find surprising. For example, I helped a team of some of our students and some collaborators on actually breaking the world record for training. Remember I mentioned the ImageNet dataset? Lots of people want to train on the ImageNet dataset. We smashed the world record for how quickly you can train it. We use standard AWS cloud infrastructure, cost of $40 of compute to train this model using, again, Fast AI library, the techniques that we learn in this course. So it can really take you a long way. So don't be kind of put off by this, what might seem pretty simple at first. We're going to get deeper and deeper. You can also use it for other kinds of passion project. So Helena Sarin, actually, you should definitely check out her Twitter account, Flagalista. This art is basically a new style of art that she's developed, which combines her painting and drawing with generative adversarial models to create these extraordinary results. And so I think this is super cool. I mean, she's not a professional artist. She is a professional software developer, but she just keeps on producing these beautiful results. And when she started, her art had not really been shown anywhere or discussed anywhere. Now there's recently been some quite high-profile articles describing how she is creating a new form of art. Again, this has come out of the Fast AI course that she developed these skills. Or equally important, Brad Kensler, who figured out how to make a picture of Kanye out of pictures of Patrick Stewart's head. Also something you will learn to do if you wish to. This particular style, this particular type of what's called style transfer was a really interesting tweak that allowed him to do some things that hadn't quite been done before. And this particular picture helped him to get a job as a deep learning specialist at AWS. So there you go. Another interesting example, another alumni actually worked at Splunk as a software engineer, and he designed an algorithm after like lesson 3, which basically turned out at Splunk to be fantastically good at identifying fraud. We'll talk more about it shortly. If you've seen Silicon Valley, the HBO series, the Hot Dog Not Hot Dog app, that's actually a real app you can download, and it was actually built by Tim Onglade as a Fast AI student project. So there's a lot of cool stuff that you can do. Yes, it was Emmy nominated. So I think we only have one Emmy nominated Fast AI alumni at this stage. So please help change that. All right. The other thing, is the forum threads can kind of turn into these really cool things. So Francisco, who's actually here in the audience, he's a really boring McKinsey consultant like me, right? So Francisco and I both have this shameful past that we were McKinsey consultants, but we left and we're okay now. And he started this thread saying like, oh, this stuff we've just been learning about building NLP in different languages, let's try and do lots of different languages. And he started this thing called the Language Model Zoo. And out of that, there's now been an academic competition was won in Polish that led to an academic paper, Thai state-of-the-art, German state-of-the-art. Basically, students have been coming up with new state-of-the-art results across lots of different languages, and this all is entirely being done by students working together through the forum. So please, get on the forum, but don't be intimidated Because remember, a lot of the, everybody you see on the forum, the vast majority post all the damn time, right? They've been doing this a lot, and they do it a lot of the time. And so at first it can feel intimidating because it can feel like you're the only new person there. But you're not, right? All of you people in the audience, everybody who's watching, everybody who's listening, you're all new people, right? And so when you just get out there and say like, okay, all you people getting new state-of-the-art results in German language modeling, I can't start my server. I try to click the notebook and I get an error. What do? People will help you. Okay, just make sure you provide all the information. This is the, I'm using Paperspace. This was the particular instance I tried to use. Here's a screenshot of my error. People will help you. Okay, or if you've got something to add. So if people are talking about crop yield analysis and you're a farmer and you think, oh, I've got something to add, so please mention it. Even if you're not sure it's exactly relevant, it's fine. Just get involved. And because remember, everybody else on the forum started out also intimidated, right? We all start out not knowing things. And so just get out there and try it. Okay, so let's get back and do some more coding. Yes, Rachel, do we have some questions?
Yeah, there's just a question from earlier about why you're using Resnet as opposed to Inception.
So the question is about this architecture. So there are lots of architectures to choose from, and it would be fair to say there isn't one best one. But if you look at things like the Stanford Dawnbench benchmark for ImageNet classification, you'll see in first place and second place and third place and fourth place is FastAI, Jeremy Howard from FastAI, Jeremy Howard, FastAI, Yaroslav's from the Department of Defense Innovation Team, Google, Resnet. Resnet's good enough, okay? So it's fine. There are other architectures. The main reason you might want a different architecture is if you want to do edge computing, so if you want to create a model that's going to sit on somebody's mobile phone. Having said that, even there, most of the time I reckon the best way to get a model onto somebody's mobile phone is to run it on your server and then have your mobile phone app talk to it. It really makes life a lot easier and you get a lot more flexibility. But if you really do need to run something on a low-powered device, then there are some special architectures for that. So the particular question was about Inception. That's another architecture which tends to be pretty memory intensive Resnet. So Inception tends to be pretty memory intensive, but it's okay. It's also it's not terribly resilient. One of the things we try to show you is stuff which just tends to always work, even if you don't quite tune everything perfectly. So Resnet tends to work pretty well across a wide range of different kind of details around choices that you might make. So I think it's pretty good. So we've got this trained model, and so what's actually happened, as we'll learn, is it's basically creating a set of weights. If you've ever done anything like linear regression or logistic regression, you'll be familiar with coefficients. We basically found some coefficients and parameters that work pretty well. And it took us 1 minute and 56 seconds. So if we want to start doing some more playing around and come back later, we probably should save those weights so we can save that 1 minute and 56 seconds. So you can just go learn.save and give it a name. Okay. It's going to put it in a model subdirectory in the same place the data came from. So if you save different models for different data bunches from different data sets, they'll all be kept separate. So don't worry about it. All right, so we talked about how the most important things are how to learn what goes into your model, what comes out. We've seen one way of seeing what goes in. Now let's see what comes out. Okay, so this is the other thing you need to get really good at. So to see what comes out, we can use this class called classification interpretation. And we're going to use this factory method from learner. So we pass in a learn object. So remember, a learn object knows two things. What's your data? And what is your model? It's now not just an architecture, but it's actually a trained model inside there. And that's all the information we need to interpret that model. So we just pass in the learner, and we now have a classification interpretation object. And so one of the things we can do, and perhaps the most useful things to do, is called plot top losses. So we're going to be learning a lot about this idea of loss functions shortly. But in short, a loss function is something that tells you how good was your prediction. And so specifically, that means if you predicted one class of cat with great confidence, you said, I am very, very sure that this is a Burman, but actually you were wrong, then that's going to have a high loss because you were very confident about the wrong answer. Okay, so that's what it basically means to have a high loss. So by plotting the top losses, we're going to find out what were the things that we were the most wrong on, or the most confident about, but we got wrong. So you can see here, it prints out 3 things. German shorthead, or 4 things. Beagle, 7.04, 0.92. Well, what do they mean? Perhaps we should look at the documentation. So we've already seen help, right? And help just prints out a quick little summary. But if you want to really see how to do something, use doc. And doc tells you the same information as help, but it has this very important thing, which is show in docs. So when you click on show in docs, it pops up the documentation for that method or class or function or whatever. It starts out by showing us the same information about what are the parameters it takes, along with the doc string, but then tells you more information. So in this case, amongst other things, it tells me the title of each shows the prediction, the actual, the loss, and the probability that was predicted. So for example, and you can see there's actually some code you can run. So the documentation always has working code. And so in this case, it was trying things with handwritten digits. And so the first one, it was predicted to be a 7. It was actually a 3. The loss is 5.44. And the probability of the actual class was 0.07. Okay, so we did not have a high probability associated with the actual class. I can see why it thought this was a 7, but nonetheless it was wrong. So this is the documentation, okay? And so this is your friend when you're trying to figure out how to use these things. The other thing I'll mention is if you're a somewhat experienced Python programmer, you'll find the source code of FastAI really easy to read. We try to write everything in just a small number of, much less than half a screen of code, generally 4 or 5 lines of code. If you click source, you can jump straight to the source code, right? So here is the plot top losses. And this is also a great way to find out how to use the FastAI library, because every line of code here, nearly every line of code is calling stuff from the FastAI library. Okay? So don't be afraid to look at the source code. I've got another really cool trick about the documentation that you're going to see a little bit later. Okay, so that's how we can look at these top losses, and these are perhaps the most important image classification interpretation tool that we have, because it lets us see what are we getting wrong. And quite often, like in this case, if you're a dog and cat expert, you'll realize that the things it's getting wrong are breeds that are actually very difficult to tell apart, and you'd be able to look at these and say, oh, I can see why it got this one wrong. Okay? So this is a really useful tool. Another useful tool, kind of, is to use something called a confusion matrix, which basically shows you for every actual type of dog or cat, how many times was it predicted to be that dog or cat. But unfortunately, in this case, because it's so accurate, this diagonal basically says, oh, it's pretty much right all the time. And you can see there's some slightly darker ones, like a 5 here, but it's really hard to read exactly what that combination is. So what I suggest you use is, instead of, if you've got lots of classes, don't use a confusion matrix. But this is my favorite named function in FastAI. I'm very proud of this. You can call most confused. And most confused will simply grab out of the confusion matrix the particular combinations of predicted and actual that it got wrong the most often. So in this case, the Staffordshire Bull Terrier was what it should have predicted, and instead it predicted an American Pit Bull Terrier, and so forth. It should have predicted a Siamese and actually predicted Burma. That happened 4 times. this particular combination happens 6 times. So this is, again, a very useful thing, because you can look and you can say, like, with my domain expertise, does it make sense that that would be something that was confused about? So these are some of the kinds of tools you can use to look at the output. Let's make our model better. So how do we make the model better? We can make it better using fine-tuning. So far we fitted 4 epochs, and it ran pretty quickly. And the reason it ran pretty quickly is that there was a little trick we used. These deep learning models, these convolutional networks, they have many layers. We'll learn a lot about exactly what layers are, but for now, just know it goes through computation on computation on computation on computation. What we did was we added a few extra layers to the end, and we only trained those. We basically left most of the model exactly as it was. So that's really fast. And if we're trying to build a model of something that's similar to the original pre-trained model, so in this case similar to the ImageNet data, that works pretty well. But what we really want to do is actually go back and train the whole model. So this is why we pretty much always use this 2-stage process. So by default, when we call fit or fit one cycle on a conv learner, it'll just fine-tune these few extra layers added to the end, and it'll run very fast. It'll basically never overfit. But to really get it good, you have to call unfreeze. And unfreeze is the thing that says, please train the whole model. And then I can call fit one cycle again, and the error got much worse. Okay, why? In order to understand why, we're actually going to have to learn more about exactly what's going on behind the scenes. So let's start out by trying to get an intuitive understanding of what's going on behind the scenes. And again, we're going to do it by looking at pictures. We're going to start with this picture. These pictures come from a fantastic paper by Matt Zeiler, who nowadays is CEO of Clarify, which is a very successful computer vision startup, and his supervisor of his PhD, Rob Fergus. And they created a paper showing how you can visualize the layers of a convolutional neural network. So a convolutional neural network will learn mathematically about what the layers are shortly, but the basic idea is that your red, green, and blue pixel values, that are numbers from 0 to 255, go into a simple computation, the first layer, and something comes out of that, and then the result of that goes into a second layer, and the result of that goes into a third layer, and so forth. And there can be up to 1,000 layers of a neural network. Resnet 34 has 34 layers. Resnet 50 has 50 layers. But let's look at layer 1. There's this very simple computation. It's a convolution. If you know what they are, we'll learn more about them shortly. What comes out of this first layer? Well, we can actually visualize the specific coefficients, the specific parameters, by drawing them as a picture. There's actually a few dozen of them in the first layer, so we won't draw all of them, but let's just look at 9 at random. So here are 9 examples of the actual coefficients from the first layer. And so these operate on groups of pixels that are next to each other. And so this first one basically finds groups of pixels that have a little diagonal line in this direction. This one finds diagonal lines in the other direction. This finds gradients that go from yellow to blue in this direction. This one finds gradients that go from pink to green in this direction, and so forth. And so they're very, very simple little filters. That's layer 1 of a ImageNet pre-trained convolutional neural net. Layer 2 takes the results of those filters and does a second layer of computation. And it allows it to create, so here are 9 examples of kind of a way of visualizing this, one of the second layer features. And you can see it's basically learned to create something that looks for corners, top left corners. And this one has learned to find things that find right-hand curves. And this one has learned to find things that find little circles. Right? So you can see how layer 2, like this is the easiest way to see it. In layer 1, we have things that can find just one line. In layer 2, we can find things that have 2 lines joined up, or one line repeated. If you then look over here, these 9 show you 9 examples of actual bits of actual photos that activated this filter a lot. Right? So in other words, this little bit of function, math function here, was good at finding these kind of window corners and stuff like that. This little circly one was very good at finding bits of photos that had circles in. Okay, so this is the kind of stuff you've got to get a really good intuitive understanding for. It's like the start of my neural net's going to find simple, very simple gradients and lines. The second layer can find very simple shapes. The third layer can find combinations of those. So now we can find repeating patterns of two-dimensional objects. Or we can find kind of things that lines that join together. Or we can find, well, what are these things? Well, let's find out. What is this? Let's go and have a look at some bits of picture that activated this one highly. Oh, mainly they're bits of text, although sometimes windows. So it seems to be able to find kind of like repeated horizontal patterns. And this one here seems to be able to find kind of edges of fluffy or flowery things. This one here is kind of finding geometric patterns. Right? So layer 3 was able to take all the stuff from layer 2 and combine them together. Layer 4 can take all the stuff from layer 3 and combine them together. By layer 4, we've got something that can find dog faces. And let's see what else we've got here. Yeah, various kinds of, oh, here we are, bird legs. So you kind of get the idea. And so by layer 5, we've got something that can find the eyeballs of birds and lizards, or faces of particular breeds of dogs, and so forth. So you can see how by the time you get to layer 34, you can find specific dog breeds and cat breeds, right? This is kind of how it works. So when we first fine-tuned that pre-trained model, we kept all of these layers that you've seen so far. And we just trained a few more layers on top of all of those sophisticated features that had already been created. Right? And so now we're fine-tuning, we're going back and saying, let's change all of these. We'll start with them where they are, right? But let's see if we can make them better. Now, it seems very unlikely that we can make these layer 1 features better. Like, it's very unlikely that the definition of a diagonal line is going to be different when we look at dog and cat breeds versus the ImageNet data that this was originally trained on. So we don't really want to change layer 1 very much, if at all. Whereas the last layers, this thing of like types of dog face, seems very likely that we do want to change that. Right? So you kind of want this intuition, this understanding that the different layers of a neural network represents different levels of kind of semantic complexity. So this is why our attempt to fine-tune this model didn't work, is because we actually, by default, it trains all the layers at the same speed, right? Which is to say it'll update those like things representing diagonal lines and gradients just as much as it tries to update the things that represent the exact specifics of what an eyeball looks like. So we have to change that. Okay? And so to change it, we first of all need to go back to where we were before. Okay? We just broke this model. Right? It's much worse than it started out. So if we just go load, this brings back the model that we saved earlier. Remember we saved it as stage 1? Okay? So let's go ahead and load that back up. So that's now, our model's back to where it was before we killed it. And let's run Learning Rate Finder. We'll learn about what that is next week. But for now, just know this is the thing that figures out what is the fastest I can train this neural network at without making it zip off the rails and get blown apart. Okay, so we can call learn.lrfind, and then we can go learn.recorder.plot, and that will plot the result of our LR finder. And what this basically shows you is there's this key parameter that we're going to learn all about called the learning rate. And the learning rate basically says how quickly am I updating the parameters in my model. And you can see that what happens is, as this bottom one here shows me what happens as I increase the learning rate, and this one here shows what's the result, what's the loss. And so you can see once the learning rate gets past 10 to the negative 4, my loss gets worse. Right? So it actually so happens, in fact I can check this, if I press Shift Tab here, my learning rate defaults to 0.003. So my default learning rate is about here. So you can see why our loss got worse, right? Because we're trying to fine-tune things now, we can't use such a high learning rate. So based on the learning rate finder, I tried to pick something, well before it started getting worse. So I decided to pick 1e next 6. So I decided I'm going to train at that rate. But there's no point training all the layers at that rate, because we know that the later layers worked just fine before when we were training much more quickly. Again, it was the default, which was, to remind us, 0.003. So what we can actually do is we can pass a range of learning rates to learn.fit. And we do it like this. You use this keyword in Python. You may have come across it before. It's called slice. And that can take a start value and a stop value. And basically what this says is train the very first layers at a learning rate of 1e neg 6, and the very last layers at a rate of 1e neg 4, and then kind of distribute all the other layers across that, between those two values equally. So we're going to see that in a lot more detail, right? But basically, for now, this is kind of a good rule of thumb, is to say after you unfreeze, so this is the thing that's going to train the whole thing, pass a max learning rate parameter, pass it a slice, make the second part of that slice about 10 times smaller than your first stage. So our first stage defaulted to about 1e neg 3, so let's use about 1e neg 4. And then this one should be a value from your learning rate finder, which is well before things started getting worse. And you can see things are starting to get worse maybe about here. So I picked something that's at least 10 times smaller than that. So if I do that, then I get 0.05788. So I don't quite remember what we got before. Yeah, a bit better, right? So we've gone down from a 6.1% to a 5.7%. So that's about a 10 percentage point relative improvement with another 58 seconds of training. So I would perhaps say for most people, most of the time, these two stages are enough to get pretty much a world-class model. You won't win a Kaggle competition, particularly because now a lot of FastAI alumni are competing on Kaggle, and this is the first thing that they do. But, in practice, you'll get something that's, about as good in practice as the vast majority of practitioners can do. We can improve it by using more layers, and we'll do this next week by basically doing a Resnet 50 instead of a Resnet 34. You can try running this during the week if you want to. You'll see it's exactly the same as before, but I'm using Resnet 50 instead of Resnet 34. What you'll find is, it's very likely if you try to do this, you will get an error. And the error will be, your GPU has run out of memory. And the reason for that is that Resnet 50 is bigger than Resnet 34. And therefore it has more parameters, and therefore it uses more of your graphics card's memory, which is totally separate to your normal computer RAM. This is GPU RAM. If you're using the kind of default Salamander, AWS, and so forth suggestion, then you'll be having 16 gig of GPU memory. The card I use most of the time has 11 gig of GPU memory. The cheaper ones have 8 gig of GPU memory. And that's kind of the main range you tend to get. If yours has less than 8 gig of GPU memory, it's going to be frustrating for you. Anyway, so you'll be somewhere around there. And it's very likely that when you try to run this, you'll get an out-of-memory error. And that's because it's just trying to do too many parameter updates for the amount of RAM you have. And that's easily fixed. This image data bunch constructor has a parameter at the end, batch size, BS for batch size. And this basically says, how many images do you train at one time? If you run out of memory, just make it smaller. Okay? So this worked for me on an 11 gig card. It probably won't work for you if you've got an 8 gig card. If you do, just make that 32. It's fine to use a smaller batch size. It might take a little bit longer. That's all. Okay? If you've got a bigger, like a 16 gig, you might be able to get away with 64. Okay? So that's just one number you'll need to try during the week. And again, we feed it for a while, and we get down to a 4.4% error rate. So this is pretty extraordinary. I was pretty surprised because, when we first did in the first course just cats versus dogs, we were kind of getting somewhere around a 3% error for something where you've got a 50% chance of being right, and the two things look totally different. So the fact that we can get a 4.4% error for such a fine-grained thing, it's quite extraordinary. In this case, I unfroze it and fit it a little bit more, went from 4.4 to 4.35, it's a tiny improvement. Basically, ResNet 50 is already a pretty good model. It's interesting because, again, you can call most confused here, and you can see the kinds of things that it's getting wrong. And I actually, depending on when you run it, you're going to get slightly different numbers, but you'll get roughly the same kinds of things. So quite often I find that ragdoll and Berman are things that it gets confused, and I actually have never heard of either of those things. So I actually looked them up on the internet, and I found a page on the cat site called "Is This a Berman or a Ragdoll?" And there is a long thread of cat experts like arguing intensely about which it is. So I feel fine that my computer had problems. I found something similar. I think it was this Pit Bull versus Staffordshire Bull Terrier. Apparently the main difference is like the particular kennel club guidelines as to how they are assessed. But some people think that one of them might have a slightly redder nose. So this is the kind of stuff where actually, even if you're not a domain expert, it helps you become one, right? Because I now know more about which kinds of pet breeds are hard to identify than I used to. So model interpretation works both ways. So what I want you to do this week is to run this notebook, make sure you can get through it. But then what I really want you to do is to get your own image data set. And actually, Francisco, who I mentioned earlier, he started the Language Do model thread, and he's now helping to TA the course. He's actually putting together a guide that will show you how to download data from Google Images, so you can create your own data set to play with. But before I do, I want to...
There's also one more question.
Okay, I'll come back to that in a moment. Before I do, I want to show you how to create labels in lots of different ways, because your data set, wherever you get it from, won't necessarily be that kind of regex-based approach. It could be in lots of different formats. So to show you how to do this, I'm going to use the MNIST sample. MNIST is pictures of hand-drawn numbers. Just because I want to show you different ways of creating these data sets. The MNIST sample basically looks like this. So I can go path.ls, okay? And you can see it's got a training set and a validation set already. So basically the people that put together this data set have already decided what they want you to use as a validation set. Okay, so if we go path/train.ls, you'll see there's a folder called 3 and a folder called 7. Right? Now this is really, really common way to give people labels. It's basically to say, oh, everything that's a 3, I'll put in a folder called 3. Everything that's a 7, I'll put in a folder called 7. Right? This is often called an ImageNet style data set, because this is how ImageNet is distributed. So if you have something in this format where the labels are just whatever the folder's called, you can say from folder. Okay? And that will create an image data bunch for you. And as you can see, 3, 7, it's created the labels just by using the folder names. Another possibility, and as you can see, we can train that, get 99.55% accuracy, blah, blah, blah. Another possibility, and for this MNIST sample I've got both, it might come with a CSV file that would look something like this. For each file name, what's its label? Now in this case, the labels aren't 3 or 7, they're 0 or 1, which is basically, is it a 7 or not? Right? So that's another possibility. So if this is how your labels are, you can use from CSV. And if it's called labels.csv, you don't even have to pass in a file name. If it's called anything else, then you can pass in the CSV labels file name. Okay, so that's how you can use a CSV. Again, there it is. This is now, is it a 7 or not? Another possibility, and then you can call data.classes to see what it found. Another possibility is, as we've seen, is you've got paths that look like this. And so in this case, this is the same thing. These are the folders, right? I could actually grab the label by using a regular expression And so here's the regular expression. So we've already seen that approach. And again, you can see data.classes has found it. So what if it's something that's in the file name or the path, but it's not just a regular expression, it's more complex? You can create an arbitrary function that extracts a label from the file name or path. And in that case, you would say from name and function. Another possibility is that you did something even more flexible than that, and so you're going to write some code to create an array of labels. And so in that case, you can just pass in from lists. So here I've created an array of labels. Here are my labels. Here's from lists, okay? And then I just pass in that array. So you can see there's lots of different ways of creating labels. So during the week, try this out. Now you might be wondering, how would you know to do all these things? Like, where am I going to find this kind of information, right? How do you possibly know to do all this stuff? So I'll show you something incredibly cool. Let's grab this function. And do you remember, to get documentation, we type doc. And here's the documentation for the function, and I can click show in docs. And it pops up the documentation. So here's the thing. Every single line of code I just showed you, I took it this morning and I copied and pasted it from the documentation. So you can see here the exact code that I just used. So the documentation for FastAI doesn't just tell you what to do, but step to step how to do it. And here is perhaps the coolest bit. If you go to FastAI, FastAI_docs, and click on docs source, it turns out that all of our documentation is actually just Jupyter notebooks. So in this case, I was looking at vision.data. So here is the vision.data notebook. You can download this repo, you can git clone it, and if you run it, you can actually run every single line of the documentation yourself. Okay, so all of our docs is also code. And so like this is the kind of the ultimate example to me of experimenting, right? Is that you can now experiment, and you'll see in GitHub it doesn't quite render properly because GitHub doesn't quite know how to render notebooks properly. But if you git clone this and open it up in Jupyter, you can see it. And so now, anything that you read about in the documentation, nearly everything in the documentation has actual working examples in it with actual data sets that are already sitting in there in the repo for you. And so you can actually try every single function in your browser. Try seeing what goes in and try seeing what comes out.
There's a question, will the library use multi-GPU in parallel by default?
The library will use multiple CPUs by default, but just one GPU by default. We probably won't be looking at multi-GPU until part 2. It's easy to do, and you'll find it on the forum, but most people won't be needing to use that now.
And the second question is whether the library can use 3D data, such as MRI or CAT scan.
Yes, it can, and there is actually a forum thread about that already. Although that's not as developed as 2D yet, but maybe by the time the MOOC is out, it will be. So before I wrap up, I'll just show you an example of the kind of interesting stuff that you can do by doing this kind of exercise. Remember earlier I mentioned that one of our alums who works at Splunk, which is a NASDAQ-listed, big, successful company, created this new anti-fraud software. This is actually how he created it as part of a FastAI Part 1 class project. He took the telemetry of users who had Splunk Analytics installed and watched their mouse movements, and he created pictures of the mouse movements. He converted speed into color and right and left clicks into splodges. He then took the exact code that we saw with an earlier version of the software and trained a CNN in exactly the way we saw, and used that to train his fraud model. So he basically took something which is not obviously a picture, and he turned it into a picture. and got these fantastically good results for a piece of fraud analysis software. So it pays to think creatively. So if you're wanting to study sounds, a lot of people that study sounds do it by actually creating a spectrogram image and then sticking that into a component. So there's a lot of cool stuff you can do with this. So during the week, yeah, get your GPU going, try and use your first notebook, make sure that you can use lesson 1 and work through it, and then see if you can repeat the process on your own data set. Get on the forum and tell us any little success you had. It's like, oh, I spent 3 days trying to get my GPU running and I finally did. Any constraints that you hit, try it for an hour or 2, but if you get stuck, please ask. And if you're able to successfully build a model with a new data set, let us know. And I will see you next week.
Welcome to lesson 2, where we're going to be taking a deeper dive into computer vision applications and taking some of the amazing stuff that you've all been doing during the week and going even further. So let's take a look. Before we do, a reminder that we have these 2 really important topics on the forums. They're pinned at the top of the forum category. One is fact resources and official course updates. This is where if there's something useful for you to know during the course, we will post there. Nobody else can reply to that thread. So if you set that thread to watching and to notifications, you're not going to be bugged by anybody else except stuff that we think you need to know for the course. And it's got all the official information about how to get set up on each platform. Please note, a lot of people post all kinds of other tidbits about how they've set up things on previous solutions or previous courses or other places. I don't recommend you use those because these are the ones that we're testing every day and that the folks involved in these platforms are testing every day, and they definitely work. Okay, so I would strongly suggest you follow those tips. And if you do have a question about using one of these platforms, please use these discussions, not some other topic that you create, because this way people that are involved in these platforms will be able to see it and things won't get messy. And then secondly, for every lesson there will be an official updates thread for that lesson. So lesson 1 official updates, and the same thing, only Fast AI people will be posting to that. So you can watch it safely, and we'll have all the things like the videos, the notebooks, and so forth. And they're all wiki threads, so you can help us to make them better as well. So I mentioned the idea of watching a thread. So this is a really good idea, is that you can go to a thread, like particularly those official update ones, and click at the bottom, watching. Okay, and if you do that, that's going to enable notifications for any updates to that thread. Particularly if you go into, click on your little username in the top right, preferences, and turn this on, that'll give you an email as well. Okay, so any of you that have missed some of the updates so far, go back and have a look through, because we're really trying to make sure that we keep you updated with anything that we think is important. One thing which can be more than a little overwhelming is even now, after just 1 week, the most popular thread has 1.1 thousand replies. So that's an intimidatingly large number. I've actually read every single one of them, and I know Rachel has, and I know Sylvain has, and I think Francisco has. But you shouldn't need to. What you should do is click Summarize this topic, and it'll appear like this, which is all of the most liked ones will appear, and then there'll be View 31 hidden replies or whatever in between. So that's how you navigate these giant topics. That's also why it's important you click the like button, because that's the thing that's going to cause people to see it in this recommended view. So when you come back to work, hopefully you've realized by now that on the official course website, course-v3.fast.ai, you will click Returning to Work, you will click the name of the platform you're using, and you will then follow the 2 steps. Step 1 will be how to make sure that you've got the latest notebooks, and step 2 will be how to make sure you've got the latest Python library software. Okay? They all look pretty much like this, but they're slightly different from platform to platform, so please don't use some different set of commands you read somewhere else. Only use the commands that you read about here, and that will make everything very smooth. if things aren't working for you, if you get into some kind of messy situation, which we all do, just delete your instance and start again. Unless you've got mission critical stuff there, it's the easiest way just to get out of a sticky situation. And if you follow the instructions here, you really should find it works fine. So this is what I really wanted to talk about most of all, is what people have been doing this week. If you've noticed, and a lot of you have, there's been 167 people sharing their work. And this is really cool because it's pretty intimidating to put yourself out there and say, like, I'm new to all this, but here's what I've done. And so examples of things I thought was really interesting was figuring out who's talking. Is it Ben Affleck or Joe Rogan? I thought this was really interesting. This is like actually very practical. I wanted to clean up my WhatsApp downloaded images to get rid of memes. So I actually built a little neural network. I mean, how cool is that to say like, oh yeah, I've got something that cleans up my WhatsApp. It's a deep learning application I wrote last week. Why not? Like, it's so easy now. You can do stuff like this. And then there's been some really interesting projects. One was looking at the sounds data that was used in this paper. And in this paper, they were trying to figure out what kind of sound things were. And they got, as you would expect, since they published a paper, they got a state-of-the-art of nearly 80% accuracy. Ethan Sutton then tried using the lesson 1 techniques and got 80.5% accuracy. So I think this is pretty awesome. Best as we know, it's a new state-of-the-art for this problem. Maybe somebody since then has published something. We haven't found it yet. They take all of these with a slight grain of salt, but I've mentioned them on Twitter, and lots of people on Twitter follow me, so if everybody knew that there was a much better approach, I'm sure somebody would have said so. This one is pretty cool. Suvash has a new state-of-the-art accuracy for Devanagari text recognition. I think he's got it even higher than this now. And this is actually confirmed by the person on Twitter who created the data set. I don't think he had any idea. He just posted, hey, here's a nice thing I did. And this guy on Twitter was like, oh, I made that data set. Congratulations, you've got a new record. So that was pretty cool. I really like this post from Alina Harley. She describes in quite a bit of detail about the issue of them metastasizing cancers and the use of point mutations and why that's a challenging, important problem. And she's got some nice pictures describing like what she wants to do with this and like how she can go about turning this into pictures. Hey, see, this is the cool trick, right? It's the same with this sounds one, turning sounds into pictures and then using the lesson 1 approach. And here it's turning point mutations into pictures and then using the lesson 1 approach. And what did she find? It seems that she's got a new state-of-the-art result by more than 30%, beating the previous best. Somebody on Twitter who's a VP at a genomics analysis company looked at this as well and thought it looked to be a state-of-the-art in this particular point mutation one as well. So that's pretty exciting. So you can see, when we talked about last week, this idea that this simple process is something which can take you a long way. It really can. I will mention that, something like this one in particular is using a lot of domain expertise. Like it's figuring out what picture to create. I wouldn't know how to do that because I don't even really know what a point mutation is, let alone how to create, something that visually is meaningful that a CNN could recognize. But the actual deep learning side is actually pretty straightforward. Another very cool result from Simon Willison and Natalie Down. They created a Cougar or Not web application over the weekend and won the Science Hack Day award in San Francisco. And so I think that's pretty fantastic. So lots of examples of people doing really interesting work. Hopefully this will be inspiring to you to think, wow, this is cool that I can do this with what I've learned. It can also be intimidating to think like, wow, these people are doing amazing things. But it's important to realize out of the thousands of people doing this course, I'm just picking out the kind of a few of the really amazing ones. And in fact, Simon is one of these very annoying people like Christine Payne, who we talked about last week, who seems to be good at everything he does. He created Django, one of the world's most popular web frameworks. He founded a very successful startup and blah, 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 blah. So, you know, one of these really annoying people who tends to keep being good at things. Now it turns out he's good at deep learning as well. So, you know, that's fine. You know, Simon can go and win a hackathon on his first week of playing with deep learning. Maybe it'll take you 2 weeks to win your first hackathon. That's okay. And I think it's important to mention this because there was this really inspiring blog post this week from James Dellinger, who talked about how he created a bird classifier using the techniques from lesson 1. But what I really found interesting was at the end, he said he nearly didn't start on deep learning at all, because he went to the scikit-learn website, which is one of the most important libraries of Python, and he saw this. And he describes in this blog post about how he was just like, that's not something I can do, that's not something I understand. And then this kind of realization of oh, I can do useful things without reading the Greek. So I thought that was a really cool message. And I really want to highlight, actually, Daniel Armstrong on the forum, I think really is a great role model here, which was he was saying, I want to contribute to the library. And I looked at the docs, and I just found it overwhelming. And his next message 1 day later was, I don't know what any of this is. I didn't know how much there was to it. It caught me off guard. My brain shut down. But I love the way it forces me to learn so much. And then 1 day later, I just submitted my first pull request. So I think that's awesome, right? It's this kind of it's okay to feel intimidated. There's a lot, right? But just pick one piece and dig into it. You know, try and push a piece of code or a documentation update or create a classifier or whatever. So here's lots of cool classifiers people have built. It's been really, really inspiring. Trinidad and Tobago Islander versus Masquerader classifier, a zucchini versus cucumber classifier. This one was really nice. This was taking the dog and cat breeds thing from last week and actually doing some exploratory work to see what the main features were, and discovered that they could now create a hairiness and classifier. And so here we now have the most hairy dogs and the most bald cats. So there are, interesting things you can do with interpretation. Somebody else on the forum took that and did the same thing for anime to find that they had accidentally discovered an anime hair color classifier. We can now detect the new versus the old Panamanian buses correctly. Apparently these are the new ones. I much prefer the old ones, but maybe that's just me. This was really interesting. Henry Palacci discovered that he can recognize with 85% accuracy which of 110 countries a satellite image is of, which is definitely got to be beyond human performance of just about anybody. I can't imagine anybody who can do that in practice. So that was fascinating. Batik cloth classification with 100% accuracy. Dave Lawar did this interesting one. He actually went a little bit further using some techniques we'll be discussing in the next couple of courses to build something that can recognize complete or incomplete or foundation buildings and actually plot them on aerial satellite view. So lots and lots of fascinating projects. So don't worry, it's only been 1 week. It doesn't mean everybody has to have had a project out yet. A lot of the folks who already have a project out have done a previous course, so they've got a bit of a head start. But we'll see today how you can definitely create your own classifier this week. So from today, after we dig a bit deeper into really how to make these computer vision classifiers in particular work well, we're then going to look at the same thing for text. We're then going to look at the same thing for tabular data, so kind of more like spreadsheets and databases. Then we're going to look at collaborative filtering, so kind of recommendation systems. That's going to take us into a topic called embeddings, which is basically a key underlying platform behind these applications. That will take us back into more computer vision and then back into more NLP. So the idea here is that it turns out that it's much better for learning if you kind of see things multiple times. So rather than being like, okay, that's computer vision, you won't see it again for the rest of the course, we're actually going to come back to the two key applications, NLP and computer vision, a few weeks apart, And that's going to force your brain to realize, like, oh, I have to remember this. It's not just something I can throw away. So we are, for people who have more of a hard sciences kind of background in particular, a lot of folks find this, hey, here's some code, type it in, start running it approach, rather than here's lots of theory approach, confusing and surprising and odd at first. And so for those of you, I just wanted to remind you, this basic tip, which is keep going. Now, you're not expected to remember everything yet. You're not expected to understand everything yet. You're not expected to know why everything works yet. You just want to be in a situation where you can enter the code and you can run it and you can get something happening, and then you can start to experiment and you kind of get a feel for what's going on. And then push on, right? Most of the people who have done the course and have gone on to be really successful watch the videos at least 3 times. So they kind of go through the whole lot and then go through it slowly the second time, and then they go through it really slowly the third time. And I consistently hear them say, I get a lot more out of it each time I go through. So don't pause at lesson 1 and stop until you can continue. Right? Yeah. So this approach is based on a lot of research, academic research into learning theory. And one guy in particular, David Perkins from Harvard, has this really great analogy. He's a researcher into learning theory. He describes this approach of the whole game, which is basically if you're teaching a kid to play soccer, you don't, first of all teach them about, how the friction between a ball and grass works, and then teach them how to sew a soccer ball with their bare hands, and then teach them the mathematics of parabolas when you kick something in the air. No, you say, here's a ball. Let's watch some people playing soccer. Okay, now we'll play soccer. And then you gradually over the following years learn more and more so that you can get better and better at it. So this is kind of what we're trying to get you to do, is to play soccer, which in our case is to type code and look at the inputs and look at the outputs. Okay, so let's dig into our first notebook, which is called Lesson 2 Download. And what we're going to do is we're going to see how to create your own classifier with your own images. So it's going to be a lot like last week's pet detector, but it'll detect whatever you like. So it'll be like those some of those examples we just saw. How would you create your own Panama bus detector from scratch? So this is inspired, the approach is inspired by Adrian Rosebrock, who has a terrific website called PyImageSearch, and he has this nice explanation of how to create a data set using Google Images. So that was definitely an inspiration for some of the techniques we use here. So thank you to Adrian. And you should definitely check out his site. It's full of lots of good resources. So, so here we are. So we are going to try to create a teddy bear detector. Thanks. We're going to try and make a teddy bear detector, and we're going to try and separate teddy bears from black bears from grizzly bears. This is very important. I have a 3-year-old daughter, and she needs to know what she's dealing with. In our house, you would be surprised at the number of monsters, lions, and other terrifying threats that are around, particularly around Halloween. And so we always need to be on the lookout to make sure that the thing we're about to cuddle is in fact a genuine teddy bear. Okay, so let's deal with that situation as best as we can. So our starting point is to find some pictures of teddy bears so we can learn what they look like. So I go to images.google.com and I type in teddy bear, and I just scroll through until I kind of find a goodly bunch of them. And it's like, okay, that looks like plenty of teddy bears to me. So then I'll go back to here. So you can see it says search and scroll. Go to Google Images and search. And the next thing we need to do is to get a list of all of the URLs there. And so to do that, you back in your Google Images, you hit Control-Shift-J or Command-Option-J, and you paste this into the window that appears. So I've got Windows, so I go Control Shift J, paste in that code. So this is a JavaScript console. For those of you who haven't done any JavaScript before, I hit Enter, and it downloads my file for me. So I would call this teddies.txt and press Save. Okay, so I now have a file of teddies, or URLs of teddies. So then I would repeat that process for black bears and for brown bears, since that's the classifier I would want, and I'd put each one in a file with an appropriate name. So that's step one. So step two is we now need to download those URLs to our server. Because remember, when we're using Jupyter Notebook, it's not running on our computer, it's running on SageMaker or Cressel or Google Cloud or whatever. So to do that, we start running some Jupyter cells. So let's grab the FastAI library, and let's start with black bears. I've already got my black bears URL. So I'll click on this cell for black bears, and I'll run it. See here how I've got 3 different cells with doing the same thing but different information. This is one way I like to work with Jupyter Notebook. It's something that a lot of kind of people with a more strict scientific background are horrified by. This is not reproducible research. I actually click here and I run this cell to create a folder called black and a file called URLs black for my black bears. I skip the next 2 cells and then I run this cell to create that folder. Okay, and then I go down to the next section and I run the next cell, which is download images for black bears. Right, so that's just going to download my black bears to that folder. And then I'll go back and I'll click on teddies and I'll run that cell and then scroll back down and I'll run this cell. And so that way I'm just going backwards and forwards to download each of the classes that I want. Very manual, but for me, I'm very iterative, I'm very experimental. That works well for me. If you're better at kind of planning ahead than I am, you can, write a proper loop or whatever and do it that way. But when you see my notebooks and see things where there's these kind of like configuration cells doing the same thing in different places, this is a strong sign that I didn't run this in order, right? I clicked one place, went to another, ran that, went back, went back, went back. And for me, I'm an experimentalist. I really like to experiment in my notebook. I treat it like a lab journal. I try things out and I see what happens. And so this is how my notebooks end up looking. It's a really controversial topic. Like for a lot of people, they feel this is like wrong, that you should only ever run things top to bottom. Everything you should do should be reproducible. For me, I don't think that's the best way of using human creativity. I think human creativity is best inspired by trying things out, seeing what happens, and fiddling around. So you can see how you go, see what works for you. So that will download the images to your server. It's going to use multiple processors to do so, and one problem there is if there's something goes wrong, it's a bit hard to see what went wrong. So you can see in the next section there's a commented out section that says max workers equals 0, and that'll do it without spinning up a bunch of processes and will tell you the errors better. So if things aren't downloading, try using the second version. Okay, so it takes, so I grabbed a small number of each, and then the next thing that I found I needed to do was to remove the images that aren't actually images at all. And this happens all the time. There's always a few images in every batch that are corrupted for whatever reason. Google image told us that this URL had an image, but actually it doesn't anymore. So we've got this thing in the library called verify images, which will check all of the images in a path, and will tell you if there's a problem. If you say delete equals true, it will actually delete it for you. Okay, so that's a really nice, easy way to end up with a clean data set. So at this point, I now have a bears folder containing a grizzly folder and a teddies folder and a black folder. In other words, I have the basic structure we need to create an image data bunch to start doing some deep learning. So let's go ahead and do that. Now, very often when you download a data set from like Kaggle or from some academic data set, there will often be a folder called train and a folder called valid and a folder called test, right, containing the different data sets. In this case, we don't have a separate validation set because we just grab these images from Google search, right? But you still need a validation set, otherwise you don't know how well your model is going. And we'll talk more about this in a moment. So whenever you create a data bunch, if you don't have a separate training and validation set, then you can just say, okay, well the training set is in the current folder, because by default it looks in a folder called train, and I want you to set aside 20% of the data, please. So this is going to create a validation set for you automatically and randomly. You'll see that whenever I create a validation set randomly, I always set my random seed to something fixed beforehand. This means that every time I run this code, I'll get the same validation set. So in general, I'm not a fan of making my machine learning experiments reproducible, i.e. ensuring I get exactly the same result every time. The randomness is, to me, really important. A really important part of finding out, is your solution stable? You know, is it going to work like each time you run it? But what is important is that you always have the same validation set, right? Otherwise, when you're trying to decide, has this hyperparameter change improved my model, but you've got a different set of data you're testing it on, then you don't know, maybe that set of data just happens to be a bit easier, right? So that's why I always set the random seed here. So we've now got, let's run that cell. So we've now got a data bunch. And so you can look inside at the data.classes and you'll see these are the folders that we created. So it knows that the classes, or, you know, so by classes we mean all the possible labels, black bear, grizzly bear, or teddy bear. We can run show batch, and we can take a little look. And it tells us straight away that some of these are going to be a little bit tricky. So this is not a photo, for instance. Some of them kind of cropped funny. Some of them might be tricky, like if you ended up with a black bear standing on top of a grizzly bear, that might be tough. Anyway, so you can kind of double check here, data.classes, there they are. Remember, C is the attribute which for classifiers tells us how many possible labels there are. We'll learn about some other more specific meanings of C later. We can see how many things are in our training set. We can see how many things are in our validation set. So we've got 473 training set, 141 validation set. So at that point we can go ahead. You'll see all these commands are identical to the PET classifier from last week. We can create our CNN, our convolutional neural network, using that data. I tend to default to using a Resnet 34, and let's print out the error rate each time and run fit one cycle 4 times and see how we go. And we have a 2% error rate. So that's pretty good. I personally aren't, I mean, sometimes it's easy for me to recognize a black bear from a grizzly bear, but sometimes it's a bit tricky. This one seems to be doing pretty well. Okay, so after I kind of make some progress with my model and things are looking good, I always like to save where I'm up to save me the 54 seconds of going back and doing it again. And as per usual, we unfreeze the rest of our model. We're going to be learning more about what that means during the course. And then we run the learning rate finder and plot it. It tells you exactly what to type. And we take a look. Now, we're going to be learning about learning rates today, actually. But for now, here's what you need to know. On the learning rate finder, what you're looking for is the strongest downward slope that's kind of sticking around for quite a while, right? So this one here looks more like a bump, but this looks like an actual downward slope to me. So it's kind of like, it's something you're going to have to practice with and get a feel for, like which bit works. So like if you're not sure, is it this bit or this bit, try both learning rates and see which one works better. Okay, but I've been doing this for a while and I'm pretty sure this looks like where it's really learning properly. So I would pick something, okay, here it's not so steep, so I would probably pick something back here for my learning rate. So you can see I picked 3e neg 5, So, you know, somewhere around here. That sounds pretty good. So that's for my bottom learning rate. For my top learning rate, I normally pick, you know, 1e neg 4 or 3e neg 4. It's kind of like I don't really think about it too much. That's a rule of thumb. It always works pretty well. One of the things you'll realize is that most of these parameters don't actually matter that much in detail. If you just copy the numbers that I use each time, the vast majority of the time it'll just work fine. And we'll see places where it doesn't today. Okay, so we've got a 1.4% error rate after doing another couple of epochs. So that's looking great. So we've downloaded some images from Google Image Search, created a classifier. We've got a 1.4% error rate. Let's save it. And then as per usual, we can use the classification interpretation class to have a look at what's going on. And in this case, we made one mistake. There was one black bear classified as a grizzly bear. So that's a really good step. We've come a long way. But possibly you could do even better if your data set was less noisy. Like maybe Google Image Search didn't give you exactly the right images all the time. So how do we fix that? And so we want to clean it up. And so combining a human expert with a computer learner is a really good idea. Almost not nobody, but very, very few people publish on this. Very, very few people teach this. But to me, it's like the most useful skill, particularly for you. You know, most of the people watching this are domain experts, not computer science experts. And so this is where you can use your knowledge of, you know, point mutations in genomics or Panamanian buses or whatever. So let's see how that would work. What I'm going to do is, do you remember the plot top losses from last time where we saw the images which it was like either the most wrong about or the least confident about? We're going to look at those and decide which of those are noisy. Like if you think about it, it's very unlikely that if there is some mislabeled data, that it's going to be predicted correctly and with high confidence. That's really unlikely to happen. So we're going to focus on the ones which the model is saying either it's not confident of or it was confident of and it was wrong about. They are the things which might be mislabeled. Big shout out to the San Francisco FastAI study group who created this new widget this week called the file deleter. That's Zach and Jason and Francisco built this thing where we basically can take the top losses from that interpretation object we just created, right? And then what we're going to do is we're going to say, okay, that returns top losses. There's not just plot top losses, but there's also just top losses. And top losses returns two things, the losses of the things that were the worst, and the indexes into the data set of the things that were the worst. And if you don't pass anything at all, it's going to actually return the entire data set, but sorted. So the first things will be the highest losses. As we'll learn during the course, or we'll keep seeing during the course, every data set in FastAI has an X and a Y. And the X contains the things that are used to, in this case, get the images. So this is the image file names, and the Ys will be the labels. So if we grab the indexes and pass them into the data set X, this is going to give us the file names of the data set ordered by which ones had the highest loss. So which ones it was either confident and wrong about or not confident about. And so we can pass that to this new widget that they've created called the file deleter widget. So just to clarify, this top loss paths contains all of the file names in our data set. When I say in our data set, this particular one is in our validation data set. So what this is going to do is it's going to clean up mislabeled images or images that shouldn't be there. And we're going to remove them from a validation set so that our metrics will be more correct. You then need to rerun these two steps, replacing valid DS with train DS, to clean up your training set to get the noise out of that as well. So it's a good practice to do both. We'll talk about test sets later as well. If you also have a test set, you would then repeat the same thing. So we run file deleter passing in that sorted list of paths. And so what pops up is basically the same thing as plot top losses. So in other words, these are the ones which is either wrong about or least confident about. And so not surprisingly, this one here does not appear to be a teddy bear or a black bear or a brown bear, right? So this shouldn't be in our data set. So what I do is I whack on the delete button, okay? And all the rest do look indeed like bears, and then so I can click confirm, and it'll bring up another 5. What's that? That's not a bear, is it? Does anybody know what that is? I'm going to say that's not a bear. Delete, confirm. Oh, not bear. Well, that's a teddy bear. I'll leave that. That's not really. I'll get rid of that one. Confirm. Okay, so what I tend to do when I do this is I'll keep going confirm until I get to a couple of screenfuls of things that all look okay. And that suggests to me that I've kind of got past the worst bits of the data. Okay, and that's it. And so now you can go back, once you do it for the training set as well, and retrain your model. So I'll just note here that what our San Francisco study group did here was that they actually built a little app inside Jupyter Notebook, which you might not have realized is possible. But not only is it possible, it's actually surprisingly straightforward. And just like everything else, you can hit double question mark to find out their secrets. So here is the source code, okay? And really, if you've done any GUI programming before, it'll look incredibly normal. You know, there's basically callbacks for what happens when you click on a button, where you just do standard Python things, and to actually render it, you just use widgets, and you can lay it out using standard boxes and whatever. So this idea of creating applications inside notebooks is like, it's really underused, but it's super neat because it lets you create tools for your fellow practitioners, for your fellow experimenters, right? And you could definitely envisage taking this a lot further. In fact, by the time you're watching this on the MOOC, you'll probably find that there's a whole lot more buttons here because we've already got a long list of to-dos that we're going to add to this particular thing. So that's it. So I think like I'd love for you to have a think about, now that you know it's possible to write applications in your notebook, what are you going to write? And if you Google for IPy widgets, you can learn about the little GUI framework to find out what kind of widgets you can create and what they look like and how they work, and so forth. And you'll find it's actually a pretty, complete GUI programming environment that you can play with, and this will all work nicely with your models and so forth. It's not a great way to productionize an application because it is sitting inside a notebook. This is really for things which are going to help other practitioners, other experimentalists, and so forth. For productionizing things, you need to actually build a production web app, which we'll look at next. Okay, so after you have cleaned up your noisy images, you can then retrain your model, and hopefully you'll find it's a little bit more accurate. One thing you might be interested to discover when you do this is it actually doesn't matter most of the time very much. On the whole, these models are pretty good at dealing with moderate amounts of noisy data. The problem would occur is if your data was not randomly noisy, but biased noisy. So I guess the main thing I'm saying is if you go through this process of cleaning up your data and then you rerun your model and find it's like 0.001% better, that's normal. Okay, it's fine, but it's still a good idea just to make sure that you don't have too much noise in your data in case it is biased. So at this point, we're ready to put our model in production. And this is where I hear a lot of people ask me about, which mega Google, Facebook, highly distributed serving system they should use, and how do they use 1,000 GPUs at the same time, and whatever else. For the vast majority of things that you all do, you will want to actually run in production on a CPU, not a GPU. Why is that? Because a GPU is good at doing lots of things at the same time. But unless you have a very busy website, it's pretty unlikely that you're going to have 64 images to classify at the same time to put into a batch into a GPU. And if you did, you've got to deal with all that queuing and running it all together. All of your users have to wait until that batch has got filled up and run. It's a whole lot of hassle, right? And then if you want to scale that, there's another whole lot of hassle. It's much easier if you just grab one thing, throw it at a CPU to get it done, and it comes back again. So yes, it's going to take, maybe 10 or 20 times longer, right? So maybe it'll take 0.2 seconds rather than 0.01 seconds. That's about the kind of times we're talking about. But it's so easy to scale, right? You can chuck it on any standard serving infrastructure. It's going to be cheap as hell. You can horizontally scale it really easily, right? So most people I know who are running apps that aren't kind of at Google scale based on deep learning are using CPUs. And the term we use is inference, right? So when you're not training a model, but you've got a trained model and you're getting it to predict things, we call that inference. So that's why we say here you probably want to use CPU for inference. So at inference time, you've got your pre-trained model, you saved those weights, and how are you going to use them to create something like Simon Willison's Cougar detector? Well, first thing you're going to need to know is what were the classes that you trained with, right? You need to know not just what are they, but what were the order, okay? So you will actually need to like serialize that or just type them in or in some way make sure you've got exactly the same classes that you trained with. If you don't have a GPU on your server, it will use the CPU automatically. If you want to test, if you have a GPU machine and you want to test using a CPU, you can just uncomment this line, and that tells FastAI that you want to use CPU by passing it back to PyTorch. So here's an example. We don't have a Cougar detector. We have a teddy bear detector, and my daughter Claire is about to decide whether to cuddle this friend. Okay, so what she does is she takes Daddy's deep learning model and she gets a picture of this, and here is the picture that she's uploaded to the web app. Okay, and here is a picture of the potentially cuddlesome object. And so we're going to store that in a variable called image. So open image is how you open an image in FastAI, funnily enough. Here is that list of classes that we saved earlier. And so as per usual, we created a data bunch. But this time we're not going to create a data bunch from a folder full of images. We're going to create a special kind of data bunch, which is one that's going to grab one single image at a time. So we're not actually passing it any data. The only reason we pass it a path is so that it knows where to load our model from, right? That's just the path, that's the folder that the model's going to be in. But what we do need to do is that we need to pass it the same information that we trained with. So the same transforms, the same size, the same normalization. This is all stuff we'll learn more about, but just make sure it's the same stuff that you used before. And so now you've got a data bunch that actually doesn't have any data in it at all. It's just something that knows how to transform a new image in the same way that you trained with, so that you can now do inference. So you can now create a CNN with this kind of fake data bunch, and again, you would use exactly the same model that you trained with. You can now load in those saved weights, okay? And so this is the stuff that you would do once, just once when your web app's starting up, okay? And it takes, 0.1 of a second to run this code. And then you just go learn.predict image. And it's lucky we did that because it is not a teddy bear. This is actually a black bear. So thankfully, due to this excellent deep learning model, my daughter will avoid having a very embarrassing black bear cuddle incident. So what does this look like in production? Well, I took Simon Willison's code and shamelessly stole it, made it probably a little bit worse, but basically it's going to look something like this. So Simon used a really cool web app toolkit called Starlet. If you've ever used Flask, this will look extremely similar, but it's kind of a more modern approach. And by modern, what I really mean is that you can use a wait. It basically means that you can wait for something that takes a while, such as grabbing some data, without using up a process. So for things like I want to get a prediction, or I want to load up some data, or whatever, it's really great to be able to use this modern Python 3 asynchronous stuff. So Starlet would come highly recommended for creating your web app. And so, yeah, you just create a route as per usual in a web app, and in that you say this is async to ensure that it doesn't steal a process while it's waiting for things. You open your image, you call .predict, and you return that response. And then you can use a whatever JavaScript client or whatever to show it. And that's it. That's basically the main contents of your web app. So give it a go, right? This week, even if you've never created a web application before, there's a lot of nice little tutorials online and kind of starter code. If in doubt, why don't you try Starlet? There's a free hosting that you can use. There's one called Python Anywhere, for example. The one that Simon's used, we'll mention that on the forum. It's something you can basically package it up as a Docker thing and shoot it off, and it'll serve it up for you. So it doesn't even need to cost you any money. And so all these classifiers that you're creating, you can turn them into web applications. So I'll be really interested to see what you're able to make of that. That'll be really fun. Okay, so let's take a break. We'll come back at 7:35. See you then. Okay, so let's move on. So I mentioned that most of the time, the kind of rules of thumb I've shown you will probably work. And if you look at the Share Your Work thread, you'll find most of the time people are posting things saying, I downloaded these images, I tried this thing, it worked much better than I expected, well, that's cool. And then like 1 out of 20 says like, I had a problem. So let's have a talk about what happens when you have a problem. And this is where we're starting to start getting into a little bit of theory, because in order to understand why we have these problems and how we fix them, it really helps to know a little bit about what's going on. So first of all, let's look at examples of some problems. The problems basically will be either your learning rate is too high or low, or your number of epochs is too high or low. So we're going to learn about what those mean and why they matter. But first of all, because we're experimentalists, let's try them. All right? So let's go with our teddy bear detector, and let's make our learning rate really high. The default learning rate is 0.003. It works most of the time. So what if we try a learning rate of 0.5? That's huge. What happens? Our validation loss gets pretty damn high. Right? Remember, this is normally something that's underneath 1. Right? So if you see your validation loss do that, right, before we even learn what validation loss is, just know this. If it does that, your learning rate's too high. That's all you need to know. Okay? Make it lower. Doesn't matter how many epochs you do. And if this happens, there's no way to undo this. You have to go back and create your neural net again and fit from scratch with a lower learning rate. So that's learning rate too high. Learning rate too low. What if we use a learning rate not of 0.003, but 1e neg 5, so 0.00001, right? So this is just, I've just copied and pasted what happened when we trained before with our default error, right, with our default learning rate. And within 1 epoch, we were down to a 2 or 3% error rate. With this really low learning rate, our error rate does get better, but very, very slowly, right? And you can plot it. If you go learn.recorder is an object which is going to keep track of lots of things happening while you train. You can call plot losses to plot out the validation and training loss, and you can just see them just like gradually going down so slow. Right? So if you see that happening, then you have a learning rate which is too small. Okay, so bump it up by 10 or bump it up by 100 and try again. The other thing you'll see if your learning rate is too small is that your training loss will be higher than your validation loss. You never want a model where your training loss is higher than your validation loss. That always means you haven't fitted enough, which means either your learning rate is too low or your number of epochs is too low. So if you have a model like that, train it some more or train it with a higher learning rate. Okay? Too few epochs. So what if we train for just one epoch? Our error rate certainly is better than random. It's 5%. But look at this. The difference between training loss and validation loss. The training loss is much higher than the validation loss. So too few epochs and too low a learning rate look very similar, right? And so you can just try running more epochs. And if it's taking forever, you can try a higher learning rate. Or if you try a higher learning rate and the loss goes off to 100,000 million, then put it back to where it was and try a few more epochs. That's the balance, right? That's basically all you care about 99% of the time. And this is only the 1 in 20 times that the defaults don't work for you. Okay, too many epochs, we're going to be talking more about this, create something called overfitting. If you train for too long, as we're going to learn about, it will learn to recognize your particular teddy bears, but not teddy bears in general. Here's the thing. Despite what you may have heard, it's very hard to overfit with deep learning. So we were trying today to show you an example of overfitting, and I turned off everything. And we're going to learn all about these terms soon. I turned off all the data augmentation. I turned off dropout. I turned off weight decay. I tried to make it overfit as much as I can. I trained it on a small-ish learning rate. I trained it for a really long time. And like, maybe I started to get it to overfit, maybe. So the only thing that tells you that you're overfitting is that the error rate improves for a while and then starts getting worse again. You will see a lot of people, even people that claim to understand machine learning, tell you that if your training loss is lower than your validation loss, then you are overfitting. As you will learn today in more detail and during the rest of the course, that is absolutely not true. Any model that is trained correctly will always have train loss lower than validation loss. That is not a sign of overfitting. That is not a sign you've done something wrong. That is a sign you have done something right. Okay. The sign that you are overfitting is that your error starts getting worse. Because that's what you care about, right? You want your model to have a low error. So as long as your training and your model error is improving, you are not overfitting. How could you be? Okay? So there's basically the they're the main 4 things that can go wrong. There are some other details that we will learn about during the rest of this course. But honestly, if you stopped listening now, please don't, that would be embarrassing. And you just like, okay, I'm going to go and download images. I'm going to create CNNs with Resnet 34 or Resnet 50. I'm going to make sure that my learning rate and number of epochs is okay. And then I'm going to chuck them up in a Starlet web API. Most of the time you're done, okay? At least for computer vision. Hopefully you'll stick around because you want to learn about NLP and collaborative filtering and tabular data and segmentation and stuff like that as well. Let's now understand what's actually going on. What does it mean, loss mean? What does an epoch mean? What does learning rate mean? Because for you to really understand these ideas, you need to know what's going on. And so we're going to go all the way to the other side. Rather than creating a state-of-the-art cougar detector, we're going to go back and create the simplest possible linear model. Okay, so we're going to actually start seeing, a little bit of math. Okay, but don't be turned off. It's okay, right? We're going to do a little bit of math, but it's going to be totally fine even if math's not your thing. Because the first thing we're going to realize is that when we see a picture, like this number 8, it's actually just a bunch of numbers. It's a matrix of numbers. For this grayscale one, it's a matrix of numbers. If it was a color image, it would be have a third dimension. So when you add an extra dimension, we call it a tensor. Rather than a matrix, it would be a 3D tensor of numbers, red, green, and blue. So when we created that teddy bear detector, what we actually did was we created a mathematical function that took the numbers from the images of the teddy bears, and the mathematical function converted those numbers into, in our case, 3 numbers. A number for the probability that it's a teddy, a probability that it's a grizzly, and a probability that it's a black bear. In this case, there's some hypothetical function that's taking the pixels representing a handwritten digit and returning 10 numbers, the probability for each possible outcome, the numbers from 0 to 9. And so what you'll often see in our code and other deep learning code is that you'll find this a bunch of probabilities, and then you'll find something called max or argmax attached to it, a function called. And so what that function is doing is it's saying, find the highest number, so the highest probability, and tell me what the index is. So np.argmax or torch.argmax of this array would return this number here. Okay, we return index 8. Does that make sense? In fact, let's try it. So we know that the function to predict something is called learn.predict. Okay, so we can chuck 2 question marks before it or after it to get the source code. And here it is, right? Pred equals res result dot argmax. And then what is the class? Well, you just pass that into the classes array. So like you should find that the source code in the FastAI library can both kind of strengthen your understanding of the concepts and make sure that you know what's going on and really help you here. You got a question? Come on over.
All right, so can we have a definition of the error rate being discussed and how it is calculated? I assume it's cross-validation error.
Sure. So one way to answer the question of how is error rate calculated would be to type error rate question mark and look at the source code, and it is 1 minus accuracy. Fair enough. And so then a question might be, what is accuracy? Accuracy question mark. It is argmax. So we now know that means find out which particular thing it is, and then look at how often that equals the target. So in other words, the actual value, and take the mean. So that's basically what it is. And so then the question is, okay, well, what is that being applied to? Always in FastAI, metrics, so these things that we pass in, we call them metrics, are always going to be applied to the validation set. Okay? So anytime you put a metric here, it'll be applied to the validation set because that's your best practice, right? That's what you always want to do, is make sure that you're checking your performance on data that your model hasn't seen. And we'll be learning more about the validation set shortly. Remember, you can also type doc. If the source code is not what you want, which it might well not be, you actually want the documentation. That will both give you a summary of the types in and out of the function and a link to the full documentation where you can find out all about how metrics work and what other metrics there are and so forth. And generally speaking, you will also find links to more information where, for example, you will find complete runs through and sample code and so forth, showing you how to use all these things. So don't forget that the doc function is your friend. Okay, and also in the documentation, both in the doc function and in the documentation, you will see a source link. This is like question mark, but what the source link does is it takes you into the exact line of code in GitHub, so you can see exactly how that's implemented and what else is around it. So lots of good stuff there.
Why were you using 3s for your learning rates earlier with 3E neg 5 and 3E neg 4?
We found that 3E neg 3 is just a really good default learning rate. It works most of the time for your initial fine-tuning before you unfreeze. And then I tend to kind of just multiply from there. So I generally find then that the next stage I will pick 10 times lower than that for the second part of the slice, and whatever the LR finder found for the first part of the slice. The second part of the slice doesn't come from the LR finder. It's just a rule of thumb, which is like 10 times less than your first part, which defaults to 3E neg 3. And then the first part of the slice is what comes out of the LR finder. And we'll be learning a lot more about these learning rate details both today and in the coming lessons. But yeah, for now, all you need to remember is that in your your basic approach looked like this. It was learn.fit one cycle, some number of epochs. I often pick 4, and some learning rate, which defaults to 3E neg 3. I'll just type it out fully so you can see. And then we do that for a bit, and then we unfreeze it, right? And then we learn some more. And so this is the bit where I just take whatever I did last time and divide it by 10. And then I also write like that, and then I have to put one more number in here, and that's the number that I get from the learning rate finder, the bit where it's got the strongest slope. So that's kind of don't have to think about it, don't really have to know what's going on, rule of thumb that works most of the time. But let's now dig in and actually understand it more completely. So we're going to create this mathematical function that takes the numbers that represent the pixels and spits out probabilities for each possible class. And by the way, a lot of the stuff that we're using here, we are stealing from other people who are awesome, and so we are putting their details here. So like, please check out their work, because they've got great work that we are highlighting in our course. I really like this idea of this little animated GIF of the numbers. So thank you to Adam Geitke for creating that. And I guess that was probably on Quora by the looks of this Medium. Oh yes, it was too. That terrific Medium post. I remember. In fact, a whole series of Medium posts. So so let's look and see how we create one of these functions. And let's start with the simplest function I know, y equals ax plus b. Okay, that's a line, right? That's a line, and the gradient of the line is here, and the intercept of the line is here. Okay, so hopefully, when we said that you need to know high school math to do this course, these are the things we're assuming that you remember. If we do kind of mention some math thing, which I'm assuming you remember, and you don't remember it, don't freak out, right? Happens to all of us. Khan Academy is actually terrific. It's not just for school kids. Go to Khan Academy, find the concept that you need a refresher on, and he explains things really well. So strongly recommend checking that out. Remember, I'm just a philosophy student, right? So I, all the time, I'm trying to either remind myself about something or I never learnt something, and so we have the whole internet to teach us these things. So I'm going to rewrite this slightly. Y equals a1x plus A2. So let's just replace B with A2. I'm just going to give it a different name. Okay. So there's another way of saying the same thing. And then another way of saying that would be if I could multiply A2 by the number 1. Okay, this still is the same thing. Okay. And so now at this point, I'm actually going to say, let's not put the number 1 there, but let's put an x1 here and an x2 here, and I'll say x2 equals 1. Okay, so far this is not, this is pretty early high school math. This is multiplying by 1, which I think we can handle. Okay, so these two are equivalent with a bit of renaming. Now, in machine learning, we don't just have one equation, we've got lots, right? So if we've got some data that represents the temperature versus the number of ice creams sold, then we kind of have lots of dots. And so each one of those dots, we might hypothesize, is based on this formula, y equals a1 x1 plus a2 x2, right? And so basically there's lots of, so this is our y, this is our x. There's lots of values of y, so we can stick a little I here. And there's lots of values of x, so we can stick a little x here, okay? So the way we kind of do that is a lot like NumPy indexing, right? But rather than things in square brackets, or PyTorch indexing, rather than things in square brackets, we kind of put them down here in our kind of in a subscript to our equation, okay? So this is now saying there's actually lots of these different yi's based on lots of different xi1 and xi2, okay? But notice there's still only one of each of these. Right? So these things here are called the coefficients or the parameters. So this is our linear equation, and this is still, we're going to say that every xi2 is equal to 1. Okay. Why did I do it that way? Because I want to do linear algebra. Why do I want to do in linear algebra? Well, one reason is because Rachel teaches the world's best linear algebra course. So if you're interested, check out Computational Linear Algebra for Coders. So it's a good opportunity for me to throw in a pitch for this free course, which we make no money, but never mind. But more to the point right now, it's going to make life much easier, right? Because I hate writing loops. I hate writing code, right? I just want the computer to do everything for me. And anytime you see like these little I subscripts, that sounds like you're going to have to do loops and all kinds of stuff. But what you might remember from school is that when you've got like two things being multiplied together, and then they get added up, that's called a dot product. And then if you do that for lots and lots of different numbers I, then that's called a matrix product. So in fact, this whole thing can be written like this. Rather than lots of different yi's, we can say there's one vector called y, which is equal to one matrix called x times one vector called a. Now at this point, I know a lot of you don't remember that. So that's fine. We have a picture to show you. I don't know who created this. Oh, no, I do. Somebody called Andre Stouts created this fantastic thing called matrix multiplication.xyz. And here we have a matrix by a vector. And we're going to do a matrix vector product. Go. That times that times that plus 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 plus. That times that times that plus 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 plus. That times that times that plus 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 plus. Finished. That is what matrix vector multiplication does. In other words, it's just that, except his version is much less messy. Okay, so let's, this is actually an excellent spot to have a little break and find out what questions we have coming through our students. What are they asking, Rachel?
Okay. When generating new image data sets, how do you know how many images are enough? What are ways to measure enough?
Yeah, that's a great question. So another possible problem you have is you don't have enough data. How do you know if you don't have enough data? Because you found a good learning rate, because if you make it higher, then it goes off into massive losses. If you make it lower, it goes really slowly, so you've got a good learning rate. And then you train for such a long time that your error starts getting worse, okay? So you know that you've trained for long enough, and you're still not happy with the accuracy. It's not good enough for the, teddy bear cuddling level of safety you want. So if that happens, there's a number of things you can do, and we'll learn about some of them we'll learn pretty much all of them during this course. But one of the easiest ones is get more data. Okay, if you get more data, then you can train for longer, get a higher accuracy, lower error rate without overfitting. Unfortunately, there's no shortcut. I wish there was. I wish there was some way to know ahead of time how much data you need. But I will say this, most of the time you need less data than you think. So organizations very commonly spend too much time gathering data, getting more data than it turned out they actually needed. So get a small amount first and see how you go.
What do you do if you have unbalanced classes, such as 200 grizzlies and 50 teddies?
Nothing. Try it. It works. A lot of people ask this question about how do I deal with unbalanced data. I've done lots of analysis with unbalanced data over the last couple of years, and I just can't make it not work. It always works. So there's actually a paper that said, like, if you want to get it slightly better, then the best thing to do is to take that uncommon class and just make a few copies of it. That's called oversampling. But I haven't found a situation in practice where I needed to do that. I've found it always just works fine for me.
Once you unfreeze and retrain with one cycle again, if your training loss is still lower than your validation loss, likely underfitting, do you retrain it unfrozen again, which will technically be more than one cycle, or do you redo everything with a longer epoch per the cycle?
Hey, you guys asked me that last week. My answer's still the same. I don't know. Either's fine. If you do another cycle, then it'll kind of maybe generalize a little bit better. If you start again, do twice as long, it's kind of annoying. Depends how patient you are. It won't make much difference. For me personally, I normally just train a few more cycles. Yeah, it doesn't make much difference most of the time.
So showing the code sample where you were creating a CNN with Resnet 34 for the Grizzly Teddy classifier. It says this requires Resnet 34, which I find surprising. I had assumed that the model created by .save, which is about 85 megabytes on disk, would be able to run without also needing a copy of Resnet 34.
Yeah, and I understand. We're going to be learning all about this shortly. You don't. There's no copy of Resnet 34. Resnet 34 is actually what we call an architecture. We're going to be learning a lot about this. It's a functional form. Just like this is a linear functional form. It doesn't take up any room. It doesn't contain anything. It's just a function. Resnet 34 is just a function. It doesn't contain anything. It doesn't store anything. I think the confusion here is that we often use a pre-trained neural net that's been learnt on ImageNet. In this case, we don't need to use a pre-trained neural net. And actually, to entirely avoid that even getting created, you can actually pass pre-trained equals false, and that'll ensure that nothing even gets loaded, which will save you another 0.2 seconds, I guess. So yeah, but we'll be learning a lot more about this. So don't worry if this is a bit unclear. But the basic idea is this thing here is basically the equivalent of saying, is it a line, or is it a quadratic, or is it a reciprocal? This is just a function. This is the Resnet 34 function. It's a mathematical function. It has no doesn't take any storage, it doesn't have any numbers, it doesn't have to be loaded, as opposed to a pre-trained model. And so that's why when we did it at inference time, the thing that took space is this bit, which is where we load our parameters, which is basically saying, as we're about to find out, what are the values of A and B. We have to store those numbers. But for Resnet 34, you don't just store two numbers, you store a few million, or a few tens of millions of numbers. So why did we do all this? Well, it's because I wanted to be able to write it out like this. And the nice thing of being able to write it out like this is that we can now do that in PyTorch with no loops, single line of code, and it's also going to run faster. PyTorch really doesn't like loops, right? It really wants you to send it a whole equation to do all at once, which means you really want to try and specify things in these kind of linear algebra ways. So let's go and take a look, because what we're going to try and do then is we're going to try and take this, we're going to call it an architecture. Right? This is like the world's tiniest neural network. It's got two parameters, you know, A1 and A2. We're going to try and fit this architecture to some data. So let's jump into a notebook and generate some dots, right, and see if we can get it to fit a line somehow. And the somehow is going to be using something called SGD. What is SGD? Well, there's two types of SGD. The first one is where I said in lesson 1, hey, you should all try building these models and try and come up with something cool. And you guys all experimented and found really good stuff. So that's where the S would be student. That would be student gradient descent. So that's version 1 of SGD. Version 2 of SGD, which is what we're going to talk about today, is where we're going to have a computer try lots of things and try and come up with a really good function, and that will be called stochastic gradient descent. The other one that you hear a lot in on Twitter is stochastic grad student descent. So that's the other one that you hear. So we're going to jump into lesson 2 SGD. And so we're going to kind of go bottom up rather than top down. We're going to create the simplest possible model we can, which is going to be a linear model. And the first thing that we need is we need some data. And so we're going to generate some data. The data we're going to generate looks like this. So this might represent temperature, and this might represent number of ice creams we sell, or something like that. But we're just going to create some synthetic data that we know is following a line. And so as we build this, we're actually going to learn a little bit about PyTorch as well. So basically the way we're going to generate this data is by creating some coefficients. A1 will be 3 and A2 will be 2. And we're going to create some, like we looked at before, basically a column of numbers for our x's and a whole bunch of 1s. And then we're going to do this, x at A. What is x at A? X at A in Python means a matrix product between x and A. It actually is even more general than that. It can be a vector-vector product, a matrix-vector product, a vector-matrix product, or a matrix-matrix product. And then actually in PyTorch specifically, it can mean even more general things where we get into higher rank tensors, which we will learn all about very soon. Right? But this is basically the key thing that's going to go on in all of our deep learning. The vast majority of the time, our computers are going to be basically doing this, multiplying numbers together and adding them up, which is a surprisingly useful thing to do. Okay, so we basically are going to generate some data by creating a line, and then we're going to add some random numbers to it. But let's go back and see how we created x and A. So I mentioned that we've basically got these two coefficients, 3 and 2, and you'll see that we've wrapped it in this function called tensor. You might have heard this word tensor before. Who's heard the word tensor before? About 2/3 of you. Okay, so it's one of these words that sounds scary, And apparently, if you're a physicist, it actually is scary. But in the world of deep learning, it's actually not scary at all. Tensor means array. Okay? It means array. Now, specifically, it's an array of a regular shape. Right? So it's not an array where row 1 has 2 things and row 3 has 3 things and row 4 has 1 thing, what you call a jagged array. That's not a tensor. A tensor is any array which has a rectangular or cube or whatever, you know, a shape where every element, every row is the same length and then every column is the same length. So 4 by 3 matrix would be a tensor. A vector of length 4 would be a tensor. A 3D array of length 3 by 4 by 6 would be a tensor. That's all a tensor is. Okay, and so we have these all the time. For example, an image is a 3-dimensional tensor. It's got number of rows by number of columns by number of channels, normally red, green, blue. So for example, a kind of a VGA picture would be 640 by 480 by 3. Or actually, we do things backwards. So when people talk about images, they normally go width by height. But when we talk mathematically, we always go number of rows by number of columns. So it would actually be 480 by 640 by 3. And that will catch you out. We don't say dimensions, though, with tensors. We use one of two words. We either say rank or axes. Rank specifically means how many axes are there, how many dimensions are there. So an image is generally a rank 3 tensor. So what we've created here is a rank 1 tensor, or also known as a vector, right? But like in math, people come up with slightly different words, or actually no, they come up with very different words for slightly different concepts. Why is a 1-dimensional array a vector, and a 2-dimensional array is a matrix, and then a 3-dimensional array, does that even have a name? Not really. Doesn't have a name. Like, it doesn't make any sense. Whereas with computers, we try to have some simple, consistent naming conventions. They're all called tensors. Rank 1 tensor, rank 2 tensor, rank 3 tensor. You can certainly have a rank 4 tensor. If you've got 64 images, then that would be a rank 4 tensor of 64 by 480 by 640 by 3, for example. So tensors are very simple. They just mean arrays. And so in PyTorch, you say tensor, and you pass in some numbers, and you get back, in this case, just a list, get back a vector. Okay? So this then represents our coefficients, the slope and the intercept of our line. And so, because remember, we're not actually going to have a special case of ax plus b. Instead, we're going to say there's always this second x value, which is always 1. You can see it here, always 1, which allows us just to do a simple matrix vector product. Okay, so that's A. And then we wanted to generate this X array of data, which is going to have, we're just going to put random numbers in the first column and a whole bunch of 1s in the second column. So to do that, we basically say to PyTorch, create a rank 2 tensor. Actually, no, sorry, let's start that again. We say to PyTorch that we want to create a tensor of n by 2. So since we passed in a total of 2 things, we get a rank 2 tensor. The number of rows will be n, and the number of columns will be 2. And in there, every single thing in it will be a 1. That's what torch.ones means. And then, this is really important, you can index into that, just like you can index into a list in Python, but you can put a colon anywhere. And a colon means every single value on that axis, or every single value on that dimension. So this here means every single row. And then this here means column 0. So this is every row of column 0. I want you to grab a uniform random number. And here's another very important concept. In PyTorch, anytime you've got a function that ends in an underscore, it means don't return to me that uniform random number, but replace whatever this is being called on with the result of this function. So this takes column 0 and replaces it with a uniform random number between -1 and 1. So there's a lot to unpack there, right? But the good news is those 2 lines of code plus this one, which we're coming to, cover 95% of what you need to know about PyTorch. How to create an array, how to change things in an array, and how to do matrix operations on an array. Okay, so there's a lot to unpack, but these small number of concepts are incredibly powerful. So I can now print out the first 5 rows. Okay, so :5 is standard Python slicing syntax to say the first 5 rows. So here are the first 5 rows, 2 columns, looking like my random numbers and my ones. So now I can do a matrix product of that X by my A, add in some random numbers to add a bit of noise, and then I can do a scatter plot. And I'm not really interested in my scatter plot in this column of ones, right? They're just there to make my linear function more convenient. So I'm just going to plot my 0 index column against my y's, and there it is. PLT is what we universally use to refer to the plotting library matplotlib. And that's what most people use for most of their plotting in Python. In scientific Python, we use matplotlib. It's certainly a library you'll want to get familiar with because being able to plot things is really important. There are lots of other plotting packages. Lots of them, the other packages are better at certain things than matplotlib, but like matplotlib can do everything reasonably well. Sometimes it's a little awkward, but you know, for me, I do pretty much everything in matplotlib because there's really nothing it can't do, even though some libraries can do other things a little bit better or a little bit prettier. But it's really powerful, so once you know matplotlib, you can do everything. So here I'm asking matplotlib to give me a scatter plot of my x's against my y's, and there it is. Okay, so this is my my dummy data representing, like, you know, temperature and ice cream sales. So now what we're going to do is we're going to pretend we were given this data and we don't know that the values of our coefficients are 3 and 2. So we're going to pretend that we never knew that. We have to figure them out. Okay, so how would we figure them out? How would we draw a line to fit to this data? And why would that even be interesting? Well, we're going to look at more about why it's interesting in just a moment, but the basic idea is this. If we can find, this is going to be kind of perhaps really surprising, but if we can find a way to find those 2 parameters to fit that line to those, how many points were there? N was 100. If we can find a way to fit that line to those 100 points, we can also fit these arbitrary functions that convert from pixel values to probabilities. It'll turn out that this techniques that we're going to learn to find these 2 numbers works equally well for the 50 million numbers in Resnet 34. So we're actually going to use an almost identical approach. So that's this, and this is the bit that I found in previous classes people have the most trouble digesting. Like I often find, even after week 4 or week 5, people will come up to me and say, I don't get it. How do we actually train these models? And I'll say, it's SGD. It's that thing we saw in the notebook with the 2 numbers. It's like, yeah, but we're fitting a neural network. It's like, I know, and we can't print the 50 million numbers anymore, but it is literally identically doing the same thing. And the reason this is hard to digest is that the human brain has a lot of trouble conceptualizing of what an equation with 50 million numbers looks like and can do. So you just kind of, for now, will have to take my word for it. It can do things like recognize teddy bears. You know, these functions turn out to be very powerful. And we're going to learn a little bit more in just a moment about how to make them extra powerful. But for now, this thing we're going to learn to fit these two numbers is the same thing that we've just been using to fit 50 million numbers. Okay, so we want to find what PyTorch calls parameters, or in statistics you'll often hear called coefficients, these values of A1 and A2. We want to find these parameters such that the line that they create minimizes the error between that line and the points. So in other words, if we created, if the A1 and A2 we came up with resulted in this line, then we'd look and we'd see like how far away is that line from each point. And we'd say, oh, that's quite a long way. And so maybe there was some other A1 or A2 which resulted in this line. And then we'd say like, oh, how far away is each of those points? And then eventually we come up with, we come up with this line, and it's like, oh, in this case, each of those is actually very close. Right? So you can see how in each case we can say how far away is the line at each spot away from its point, and then we can take the average of all those, and that's called the loss. Right? That is the value of our loss. Right? So you need some mathematical function that can basically say how far away is this line from those points. For this kind of problem, which is called a regression problem, a problem where your dependent variable is continuous, so rather than being grizzlies or teddies, it's like some number between -1 and 6. This is called a regression problem. And for regression, the most common loss function is called mean squared error, which pretty much everybody calls MSE. You may also see RMSE, which is root mean squared error. And so the mean squared error is a loss. It's the difference between some prediction that you've made, okay, which is like the value at the line, and the actual number of ice cream sales. And so in the mathematics of this, people normally refer to the actual, they normally call it y, and the prediction, they normally call it y hat, as in they write it like that. Okay. And so what I try to do, like when we're writing something like a mean squared error equation, there's no point writing ice cream here and temperature here, because we want it to apply to anything. So we tend to use these like mathematical placeholders. So the value of mean squared error is simply the difference between those two squared, right? And then we can take the mean. Because remember, that is actually a vector, or what we now call it, a rank 1 tensor. And that is actually a rank 1 tensor. So it's the value of the number of ice cream sales at each place, right? So when we subtract one vector from another vector, and we're going to be learning a lot more about this, but it does something called element-wise arithmetic. In other words, it subtracts each one from each other. And so we end up with a vector of differences. And then if we take the square of that, it squares everything in that vector. And so then we can take the mean of that to find the average square of the differences between the actuals and the predicted. So if you're more comfortable with mathematical notation, what we just wrote there was the sum of, which way around did we do it? Y hat minus y squared over n. Right? So that equation is the same as that equation. So one of the things I'll note here is I don't think this is, more complicated or unwieldy than this, right? But the benefit of this is you can experiment with it. Like once you've defined it, you can use it. You can send things into it and get stuff out of it and see how it works, right? So for me, most of the time, I prefer to explain things with code rather than with math, right? Because I can actually, they're the same, right? They're doing, in this case at least, and in all the cases we'll look at, They're exactly the same, they're just different notations for the same thing. But one of the notations is executable, it's something that you can experiment with, and one of them is abstract. So that's why I'm generally going to show code. So the good news is if you're a coder with not much of a math background, actually you do have a math background because code is math, right? If you've got more of a math background and less of a code background, then actually a lot of the stuff that you learned from math is going to translate very directly into code. And now you can start to experiment really with your math. Okay, so this is a loss function. This is something that tells us how good our line is. So now we have to kind of come up with what is the line that fits through here. Because remember, we don't know. We're going to pretend we don't know. So what you actually have to do is you have to guess. You actually have to come up with a guess. What are the values of A1 and A2? So let's say we guessed that A1 and A2 are both 1. So this is our tensor. A is 1, 1. Right? So here is how we create that tensor. And I wanted to write it this way because you'll see this all the time. Like written out, it should be 1.0. Oh, sorry, it looks like we're starting with -1. -1. Written out fully, it would be -1.0, 1.0. Like that's written out fully. We can't write it without the point because that's now an int, not a floating point. So that's going to spit the dummy if you try to do calculations with that in neural nets, right? I'm lazy. I'm far too lazy to type .0 every time. Python knows perfectly well that if you add a dot next to any of these numbers, then the whole thing is now floats, right? So that's why you'll often see it written this way, particularly by lazy people like me. Okay, so A is a tensor. You can see its floating point. You see, like even PyTorch is lazy. They just put a dot. They don't bother with a 0, right? But if you want to actually see exactly what it is, you can write dot type, and you can see it's a float tensor. Okay. And so now we can calculate our predictions with this like random guess, x at A, matrix product of x and A. And we can now calculate the mean squared error of our predictions and our actuals, and that's our loss. Okay, so for this regression, our loss is 8.9. And so we can now plot a scatter plot of x against y, and we can plot a scatter plot of x against y hat, our predictions, and there they are. Okay, so this is the 1, comma -1 line. Sorry, -1, 1 line, and here's our actuals. So that's not great, which is not surprising, because it's just a guess. So SGD, or gradient descent more generally, and anybody who's done ND engineering or probably computer science at school will have done plenty of this, like Newton's method, whatever. It's all the stuff that you did at university. If you didn't, don't worry, we're going to learn it now. It's basically about taking this guess and trying to make it a little bit better. So how do we make it a little bit better? Well, there's only two numbers, right? And the two numbers are the intercept of that orange line and the gradient of that orange line. So what we're going to do with gradient descent is we're going to simply say, what if we changed those two numbers a little bit? What if we made the intercept a little bit higher or a little bit lower? What if we made the gradient a little bit more positive or a little bit more negative? So there's like 4 possibilities. And then we can just calculate the loss for each of those 4 possibilities and see what worked. Did lifting it up or down make it better? Did tilting it more positive or more negative make it better? And then all we do is we say, okay, well, whichever one of those made it better, that's what we're going to do. And that's it, right? But here's the cool thing, for those of you that remember calculus, you don't actually have to move it up and down and round about. You can actually calculate the derivative. The derivative is the thing that tells you, would moving it up or down make it better, or would rotating it this way or that way make it better? Okay. So the good news is, if you didn't do calculus or you don't remember calculus, I just told you everything you need to know about it, right? which is that it tells you how changing one thing changes the function. Right? That's what the derivative is. Kind of, not quite strictly speaking, but close enough, also called the gradient. Okay, so the gradient or the derivative tells you how changing A1 up or down would change our MSE, how changing A2 up or down would change our MSE, and it just does it more quickly. It does it more quickly than actually moving it up and down. Right? So in school, unfortunately, they forced us to sit there and calculate these derivatives by hand. We have computers. Computers can do that for us. We are not going to calculate them by hand. Instead, we're going to call .grad. On our computer, that will calculate the gradient for us. So here's what we're going to do. We're going to create a loop. We're going to loop through 100 times, and we're going to call a function called update. That function is going to calculate y hat, our prediction. It is going to calculate loss, our mean squared error. From time to time, it will print that out so we can see how we're going. It will then calculate the gradient. And in PyTorch, calculating the gradient is done by using a method called backward. So you'll see something really interesting, which is mean squared error was just a simple standard mathematical function. PyTorch, for us, keeps track of how it was calculated and lets us calculate the derivative. So if you do a mathematical operation on a tensor in PyTorch, you can call backward to calculate the derivative. What happens to that derivative? It gets stuck inside an attribute called .grad. So I'm going to take my coefficients A, and I am going to subtract from them my gradient. And there's an underscore here. Why? Because that's going to do it in place. So it's going to actually update those coefficients A to subtract the gradients from them, right? So why do we subtract? Well, because the gradient tells us if I move the whole thing downwards, the loss goes up. If I move the whole thing upwards, the loss goes down. So I want to do the opposite of the thing that makes it go up, right? So because our loss, we want our loss to be small. So that's why we have to subtract. And then there's something here called LR. LR is our learning rate. And so literally all it is the thing that we multiply by the gradient. Why is there any LR at all? Let me show you why. Let's take a really simple example. A quadratic. Right? And let's say your algorithm's job was to find where that quadratic was at its lowest point. And so how could it do this? Well, just like what we're doing now, the starting point would just be to pick some x value at random. And then pop up here to find out what the value of y is. Okay? And that's its starting point. And so then it can calculate the gradient. And the gradient is simply the slope. Right? It tells you moving in which direction is going to make you go down. And so the gradient tells you you have to go this way. So if the gradient was really big, you might jump this way a very long way. So you might jump all the way over to here, maybe even here, right? And so if you jumped over to there, then that's actually not going to be very helpful, because then you see, well, where does that take us to? Oh, it's now worse, right? We jumped too far. So we don't want to jump too far, so maybe we should just jump a little bit, maybe to here. And the good news is that is actually a little bit closer. And so then we'll just do another little jump, see what the gradient is, and do another little jump. That takes us to here. And another little jump, that takes us to here. Here, here, right? So in other words, we find our gradient, to tell us kind of what direction to go and like, do we have to go a long way or not too far? But then we multiply it by some number less than 1 so we don't jump too far. And so hopefully at this point, this might be reminding you of something, which is what happened when our learning rate was too high. So do you see why that happened now? Our learning rate was too high, meant that we jumped all the way past the right answer, further than we started with, and it got worse and worse and worse. So that's what a learning rate too high does. On the other hand, if our learning rate is too low, then you just take tiny little steps. And so eventually you're going to get there, but you're doing lots and lots of calculations along the way. So you really want to find something where it's kind of either like this, or maybe it's kind of a little bit backwards and forwards. Maybe it's kind of like this. Something like that. You know, you want something that kind of gets in there quickly, but not so quickly it jumps out and diverges, not so slowly that it takes lots of steps. So that's why we need a good learning rate. And so that's all it does. So if you look inside the source code of any deep learning library, you'll find this. You'll find something that just says coefficients dot subtract learning rate times gradient. And we'll learn about some we'll learn about some easy but important optimizations we can do to make this go faster. But that's basically it. There's a couple of other little minor issues that we don't need to talk about now, one involving zeroing out the gradients, another involving making sure that you turn gradient calculation off when you do the SGD update. If you're interested, we can discuss them on the forum. Or you can do our Introduction to Machine Learning course, which covers all the mechanics of this in more detail. But this is the basic idea. So if we run update 100 times, printing out the loss from time to time, you can see it starts at 8.9, and it goes down, 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 down. And so we can then print our scatter plots, and there it is. That's it. Believe it or not, that's gradient descent. So we just need to start with a function that's a bit more complex than x at a. But as long as we have a function that can represent things like, is this a teddy bear, we now have a way to fit it. Okay? And so let's now take a look at this as a picture, as an animation. And this is one of the nice things that you can do with Matplotlib, is you can take any plot and turn it into an animation, right? And so you can now actually see it updating each step. So let's see what we did here. We simply said, as before, create a scatter plot. But then rather than having a loop, we used Matplotlib's func animation to call 100 times this function. And this function just called that update that we created earlier, and then updated the y data in our line. And so it did that 100 times, waiting 20 milliseconds after each one, and there it is. Right? So you might think that like visualizing your algorithms with animations is some amazing and complex thing to do, but actually now you know it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines of code. Okay? So I think that is pretty damn cool. So that is SGD visualized. And so we can't visualize as conveniently what updating 50 million parameters in a Resnet 34 looks like, but it's basically doing the same thing. Okay? And so studying these simple versions is actually a great way to get an intuition. So you should try running this notebook with a really big learning rate, with a really small learning rate, and see what this animation looks like. Right? And try and get a feel for it. Maybe you can even try a 3D plot. I haven't tried that yet, but I'm sure it would work fine too. So the only difference between stochastic gradient descent and this is something called mini batches. You'll see what we did here was we calculated the value of the loss on the whole data set on every iteration. But if your data set is 1.5 million images in ImageNet, that's going to be really slow, right? Just to do a single update of your parameters, you've got to calculate the loss on 1.5 million images. You wouldn't want to do that. So what we do is we grab 64 images or so at a time at random, and we calculate the loss on those 64 images, and we update our weights. And then we grab another 64 random images, and we update the weights. So in other words, the loop basically looks exactly the same, but at this point here, it would basically be y, square bracket, and some random indexes here, and some random indexes here, and would basically do the same thing. Well, actually, sorry, it would be there, right? So some random indexes on our x and some random indexes on our y to do a mini batch at a time. That would be the basic difference. And so once you add those, grab a random few points each time. Those random few points are called your mini batch, and that approach is called SGD, or stochastic gradient descent. Okay. So there's quite a bit of vocab we've just covered, right? So let's just remind ourselves. The learning rate is a thing that we multiply our gradient by to decide how much to update the weights by. An epoch is one complete run through all of our data points, or all of our images. So for the non-stochastic gradient descent we just did, every single loop we did the entire data set. But if you've got a data set with 1,000 images and your mini batch size is 100, then it would take you 10 iterations to see every image once. So that would be one epoch. Epochs are important because if you do lots of epochs, then you're looking at your images lots of times. And so every time you see an image, there's a bigger chance of overfitting. So we generally don't want to do too many epochs. A mini batch is just a random bunch of points that you use to update your weights. SGD is just gradient descent using mini batches. Architecture and model kind of mean the same thing. In this case, our architecture is y equals xa. Right? The architecture is the mathematical function that you're fitting the parameters to. And we're going to learn either today or next week what the mathematical function of things like Resnet 34 actually is. But it's basically pretty much what you've just seen. It's a bunch of matrix products. Parameters, also known as coefficients, also known as weights, are the numbers that you're updating. And then loss function is the thing that's telling you how far away or how close you are to the correct answer. Any questions? All right. So these models, these predictors, these teddy bear classifiers are functions that take pixel values and return probabilities. They start with some functional form like y equals xa, and they fit the parameters a using SGD to try and do the best to calculate your predictions. So far we've learned how to do regression, which is a single number. Next week we'll learn how to do the same thing for classification, where we have multiple numbers, but it's basically the same. In the process, we had to do some math. We had to do some linear algebra, and we had to do some calculus. And a lot of people get a bit scared at that point and tell us, I am not a math person. If that is you, that's totally okay, but you're wrong. You are a math person. In fact, it turns out that when in the actual academic research around this, there are not math people and non-math people. It turns out to be entirely a result of culture and expectations. So you should check out Rachel's talk. There's no such thing as not a math person, where she will introduce you to some of that academic research. And so if you think of yourself as not a math person, you should watch this so that you learn that you're wrong, that your thoughts are actually there because somebody has told you you're not a math person. But there's actually no academic research to suggest that there is such a thing. In fact, there are some cultures, like Romania and China, where the not a math person concept never even appeared. It's almost unheard of in some cultures for somebody to say, I'm not a math person, because that just never entered that cultural identity. So don't freak out if words like derivative and gradient and matrix product are things that you're kind of scared of. It's something you can learn. It's something you'll be okay with. Okay. So the last thing that we're going to close with today. Oh, I just got a message from Simon Willison. Simon's telling me he's actually not that special. Lots of people won medals. So that's the worst part about Simon, is not only is he really smart, he's also really modest, which I think is just awful. I mean, if you're going to be that smart, at least be a horrible human being and, you know, make it okay. Okay, so the last thing I want to close with is the idea of, and we're going to look at this more next week, underfitting, overfitting. We just fit a line to our data. But imagine that our data wasn't actually line-shaped, right? And so if we tried to fit something which was like constant plus constant times x, i.e. a line to it, then it's never going to fit very well, right? No matter how much we change these two coefficients, it's never going to get really close. On the other hand, we could fit some much bigger equation, so in this case it's a higher degree polynomial, with lots of wiggly bits, like so, right? But if we did that, it's very unlikely we go and look at some other place to find out the temperature that it is and how much ice cream they're selling and that we'll get a good result, because like the wiggles are far too wiggly. So this is called overfitting. We're looking for some mathematical function that fits just right, to stay with the teddy bear analogies. So you might think, if you have a statistics background, the way to make things fit just right is to have exactly the right number of parameters. It's to use a mathematical function that doesn't have too many parameters in it. It turns out that's actually completely not the right way to think about it. There are other ways to make sure that we don't overfit. And in general, this is called regularization. Regularization are all the techniques to make sure that when we train our model, that it's going to work not only well on the data it's seen, but on the data it hasn't seen yet. So the most important thing to know when you've trained a model is actually how well does it work on data that it hasn't been trained with. And so as we're going to learn a lot about next week, that's why we have this thing called a validation set. So what happens with a validation set is that we do our mini batch STD training loop with one set of data, with one set of teddy bears, grizzlies, black bears. And then when we're done, we check the loss function and the accuracy to see how good is it on a bunch of images which were not included in the training. And so if we do that, then if we have something which is too wiggly, it'll tell us, oh, your loss function and your error is really bad, because on the bears that it hasn't been trained with, the wiggly bits are in the wrong spot. Or if it was underfitting, it would also tell us that your validation set's really bad. So, like, even for people that don't go through this course and don't learn about the details of deep learning, like if you've got managers or colleagues or whatever at work who are kind of wanting to like learn about AI, the only thing that you really need to be teaching them is about the idea of a validation set, because that's the thing they can then use to figure out, you know, is somebody selling them snake oil or not? You know, to like hold back some data, and then they get told like, oh, here's a model that we're going to roll out. And then you say, okay, fine. I'm just going to check it on this held out data to see whether it generalizes. There's a lot of details to get right when you design your validation set. We will talk about them briefly next week, but a more full version would be in Rachel's piece on the FastAI blog called How and Why to Create a Good Validation Set. And this is also one of the things we go into in a lot of detail in the Intro to Machine Learning course. So we're going to try and give you enough to get by for this course, but it is certainly something that's worth deeper study as well. Any questions or comments before we wrap up? Okay, good. All right, well, thanks everybody. I hope you have a great time building your web applications. See you next week.
Welcome back to lesson 3. So we're going to start with a quick correction, which is to let you know that when we referred to this chart as coming from Quora last week, we were correct. It did come from Quora, but actually we realized originally it came from Andrew Ng's excellent machine learning course on Coursera. So apologies for the incorrect citation. But in exchange, let's talk about Andrew Ng's excellent machine learning course on Coursera. It's really great. As you can see, people gave it 4.9 out of 5 stars. In some ways, it's a little dated, but a lot of the content really is as appropriate as ever and taught in a more bottom-up style. So it can be quite nice to combine Andrew's bottom-up style and our top-down style and meet somewhere in the middle. Also, if you're interested in more machine learning foundations, you should check out our machine learning course as well. If you go to course.fast.ai and click on the machine learning button, that will take you to our course, which is about twice as long as this deep learning course and kind of takes you much more gradually through some of the foundational stuff around validation sets and model interpretation and how PyTorch tensors work and stuff like that. I think all these courses together, if you want to really dig deeply into the material, do all of them. I know a lot of people who have and end up saying, oh, I got more out of each one by doing the whole lot. Or you can skip backwards and forwards, see which one works for you. We started talking about deploying your web app last week. One thing that's going to make life a lot easier for you is that on the Course V3 website, there's a production section where right now we have one platform, but more will be added by the time this video comes out, showing you how to deploy your web app really, really easily. And when I say easily, for example, here's the How to Deploy on Zeit guide created by San Francisco study group member Navjot. As you can see, it's just a page. There's almost nothing to do. And it's free. It's not going to serve 10,000 simultaneous requests, but it'll certainly get you started, and I found it works really well. It's fast, and so deploying a model doesn't have to be slow or complicated anymore. And the nice thing is you can kind of use this for an MVP, and if you do find you're starting to get 1,000 simultaneous requests, then you know that things are working out, and you can start to upgrade your instance types or add to a more traditional big engineering approach. So if you actually use this starter kit, it will actually create my teddy bear finder for you. And this is an example of my teddy bear finder. So the idea is it's as simple as possible, this template. So you can fill in your own style sheets, your own custom logic, and so forth. This is kind of designed to be a minimal thing so you can see exactly what's going on. The back end is a simple kind of REST style, interface that sends back JSON, and the front end is a super simple little JavaScript thing. Yeah, it should be a good way to get a sense of how to build a web app which talks to a PyTorch model. So examples of web apps people have built during the week. Edward Ross built the What Car Is That app, or more specifically, the What Australian Car Is That. I thought it was kind of interesting that Edward said on the forum that the building of the app was actually a great experience in terms of understanding how the model works himself better. And like it's interesting that he's describing like trying it out on his phone. And a lot of people think like, oh, if I want something on my phone, I have to create some kind of mobile TensorFlow, ONNX, whatever, tricky mobile app. You really don't. You can run it all in the cloud and make it just a web app, or use some kind of simple little GUI front end that talks to a REST backend. It's not that often that you'll need to actually run stuff on the phone. So this is a good example of that. C. Werner has created a guitar classifier. You can decide whether your food is healthy or not. Apparently this one is healthy. That can't be right. I would have thought a hamburger is more what we're looking for, but there you go. Apparently Trinidad and Tobago is the home of the hummingbird, so if you're visiting, you can find out what kind of hummingbird you're looking at. You can decide whether or not to eat a mushroom. If you happen to be one of the cousins of Charlie Harrington, you can now figure out who is who. I believe this was actually designed for his fiancée. Even will tell you about the interests of this particular cousin. So, you know, fairly niche application, but, you know, apparently there are 36 people who will appreciate this at least. I have no cousins. That's a lot of cousins. This is an example of an app which actually takes a video feed and turns it into a motion classifier. That's pretty cool. I like it. Team 26, good job. Here's a similar one for American Sign Language. And so, like, it's not a big step from taking a single image model to taking a video model. You can just grab the occasional frame, put it through your model, and update the UI as the kind of model results come in. So it's really cool that you can do this kind of stuff either in client or in browser nowadays. Henry Palacci has built Your City From.space, which he describes as creepy, how accurate it is. So here is where I live, which it figured out was in the United States. It's interesting, he describes here how he actually had to be very thoughtful about the validation set he built, make sure that the satellite tiles were not overlapping or close to each other. In doing so, he realized he had to download more data, but once he did, he got this amazingly effective model that can look at satellite imagery and figure out what country it's from. I thought this one was pretty interesting, which was doing univariate time series analysis by converting it into a picture using something I've never heard of, a gradient angular field. But he says he's getting close to state-of-the-art results for univariate time series modeling by turning it into a picture. And so I like this I like this idea of turning stuff that's not a picture into a picture. So something really interesting about this project, which was looking at emotion classification from faces, was that he was specifically asking the question, how well does it go without changing anything, just using the default settings? Which I think is a really interesting experiment because we're all told it's really hard to train models and it takes a lot of, you know, specific knowledge. And actually we're finding that that's often not the case. And he looked at this facial expression recognition data set. There was a 2017 paper that he compared his results to, and he got equal or slightly better results than the state-of-the-art paper on emotion recognition without doing any custom hyperparameter tuning at all. So that was really cool. And then Elena Harley, who I featured one of her works last week, has done another really cool work in the genomic space, which is looking at variant analysis, looking at false positives in these kinds of pictures. And she found she was able to decrease the number of false positives coming out of the kind of industry standard software she was using by 500% by using a deep learning workflow. And I think this is a nice example of something where if you're going through, you know, spending hours every day looking at something, in this case looking at, you know, kind of get rid of the false positives, maybe you can make that a lot faster by using deep learning to do a lot of the work for you. And again, this is an example of a computer vision-based approach on something which initially wasn't actually images. So that was, yeah, that's a really cool application. So really nice to see what people have been building in terms of both web apps and just classifiers. What we're going to do today is look at a whole lot more different types of model that you can build. And we're going to kind of zip through them pretty quickly, and then we're going to go back and say, like, oh, how did all these things work? What's the common denominator? But all of these things, you can create web apps from these as well, but you'll have to think about how to slightly change that template to make it work with these different applications. I think that'll be a really good exercise in making sure you understand the material. So the first one we're going to look at is a data set of satellite images. And satellite imaging is a really fertile area for deep learning. It's certainly a lot of people already using deep learning and satellite imaging, but only scratching the surface. And the data set that we're going to look at looks like this. It has satellite tiles, and for each one, as you can see, there's a number of different labels for each tile. One of the labels always represents the weather that's shown, so in this case cloudy or partly cloudy. And then all of the other labels tell you any interesting features that are seen there. So primary means primary rainforest, agriculture means there's some farming, road, and so forth. So as I'm sure you can tell, this is a little different to all the classifiers we've seen so far, because there's not just one label, there's potentially multiple labels. So multi-label classification can be done in a very similar way. But the first thing we're going to need to do is to download the data. Now this data comes from Kaggle. Kaggle is mainly known for being a competitions website, and it's really great to download data from Kaggle when you're learning, because you can see how would I have gone in that competition. And it's a good way to see whether you kind of know what you're doing. I tend to think the goal is to try and get in the top 10%. In my experience, all the people in the top 10% of a competition really know what they're doing. So if you can get in the top 10%, then that's a really good sign. Pretty much every Kaggle data set is not available for download outside of Kaggle, at least the competition data sets. So you have to download it through Kaggle. The good news is that Kaggle provides a Python-based downloader tool, which you can use. So we've got a quick description here of how to download stuff from Kaggle. So to install stuff, to download stuff from Kaggle, you first have to install the Kaggle download tool, so just pip install Kaggle. And so you can see what we tend to do when there's one-off things to do is we show you the commented out version in the notebook, and you can just remove the comment. So here's a cool tip for you. If you select a few lines and then hit Control/, it uncomments them all. And then when you're done, select them again, Control/ again, and recomments them all. Okay? So if you run this line, it'll install Kaggle for you. Depending on your platform, you may need sudo, you may need /something else, /pip, you may need source activate. So have a look on the setup instructions, or actually the returning to work instructions on the course website to see, like, when we do conda install, you have to do the same basic steps for your pip install. So once you've got that module installed, you can then go ahead and download the data. And basically, it's as simple as saying Kaggle competitions download, the competition name, and then the files that you want. The only other steps before you do that is that you have to authenticate yourself. And you'll see there's a little bit of information here on exactly how you can go about downloading from Kaggle the file containing your API authentication information. So I won't bother going through it here, but just follow these steps. Sometimes stuff on Kaggle is not just zipped or tarred, but it's compressed with a program called 7-zip, which will have a 7z extension. If that's the case, you'll need to either apt install p7zip, or, and here's something really nice, some kind person has actually created a conda installation of 7-zip that works on every platform. So you can always just run this conda install, doesn't even require sudo or anything like that. And this is actually a good example of where conda is super handy, is that you can actually install binaries and libraries and stuff like that, and it's nicely cross-platform. So that's a good, if you don't have 7-zip installed, that's a good way to get it. And so this is how you unzip a 7-zip file. In this case, it's tarred and 7-zipped, so you can do this all in one step. So 7ZA is the name of the 7-zip archiver program that you would run. Okay, so that's all basic stuff, which if you're not so familiar with the command line and stuff, it might take you a little bit of experimenting to get it working. Feel free to ask on the forum. Make sure you search the forum first to get started. Okay, so once you've got the data downloaded and unzipped, you can take a look at it. So in this case, because we have multiple labels for each tile, we clearly can't have a different folder for each image telling us what the label is. We need some different way to label it. And so the way that Kaggle did it was they provided a CSV file that had each file name along with a list of all of the labels. In order to just take a look at that CSV file, we can read it using the pandas library. If you haven't used pandas before, it's kind of the standard way of dealing with tabular data in Python. It pretty much always appears in the PD namespace. In this case, we're not really doing anything with it other than just showing you the contents of this file. So we can read it, we can take a look at the first few lines, and there it is. So we want to turn this into something we can use for modeling. So the kind of object that we use for modeling is an object of the data bunch class. So we have to somehow create a data bunch out of this. Once we have a data bunch, we'll be able to go .showBatch to take a look at it, and then we'll be able to go create CNN with it, and then we'll be able to start training. Okay? So really the trickiest step previously in deep learning has often been getting your data into a form that you can get it into a model. So far, we've been showing you how to do that using various factory methods. So methods where you basically say, I want to create this kind of data from this kind of source with these kinds of options. The problem is, I mean, that works fine sometimes, and we showed you a few ways of doing it over the last couple of weeks. But sometimes you want more flexibility, because there's so many choices that you have to make about where do the files live and what's the structure they're in and how do the labels appear and how do you split out the validation set and how do you transform it and so forth. So we've got this unique API that I'm really proud of called the data block API. And the data block API makes each one of those decisions a separate decision that you make. There's separate methods and with their own parameters for every choice that you make around how do I create, set up my data. So for example, to grab the planet data, we would say we've got a list of image files that are in a folder and they're labeled based on a CSV with this name. They have this separator. Remember I showed you back here that there's a space between them? So by passing in separator, it's going to create multiple labels. The images are in this folder. They have this suffix. We're going to randomly split out a validation set with 20% of the data. We're going to create data sets from that, which we're then going to transform with these transformations. And then we're going to create a data bunch out of that, which we'll then normalize using these statistics. So there's all these different steps. So to give you a sense of what that looks like, the first thing I'm going to do is kind of go back and explain what are all of the PyTorch and FastAI kind of classes that you need to know about that are going to appear in this process, because you're going to see them all the time in the FastAI docs and the PyTorch docs. So the first one you need to know about is a class called a dataset. And the dataset class is part of PyTorch, and this is the source code for the dataset class. As you can see, it actually does nothing at all. The dataset class in PyTorch defines two things, get item and len. In Python, these special things that are underscore, underscore something, underscore, underscore, Pythonistas call them dunder something. So this would be dunder get item, dunder len. And they're basically special magical methods that do some special behavior. This particular method, you can look them up in the Python docs. This particular method means that your object, if you had an object called O, can be indexed with square brackets, something like that, right? So that would call get item with 3 as the index. And then this one called len means that you can go len o, and it will call that method. Now, and you can see in this case, they're both not implemented. So that is to say, although PyTorch says tell PyTorch about your data, you have to create a data set. It doesn't really do anything to help you create the data set. It just defines what the data set needs to do. So in other words, your data, the starting point for your data, is something where you can say, what is the third item of data in my data set? So that's what getItem does. And how big is my data set? That's what the length does. So FastAI has lots of data set subclasses that do that for all different kinds of stuff. And so far, you've been seeing image classification data sets. So they're data sets where getItem will return an image and a single label of what is that image. So that's what a data set is. Now, a data set is not enough to train a model. The first thing we know we have to do, if you think back to the gradient descent tutorial last week, is we have to have a few images or a few items at a time so that our GPU can work in parallel. Remember, we do this thing called a mini batch. A mini batch is a few items that we present to the model at a time that it can train from in parallel. So to create a mini batch, we use another PyTorch class called a data loader. And so a data loader takes a data set in its constructor. So it's now saying, oh, this is something I can get the third item and the fifth item and the ninth item. And it's going to grab items at random and create a batch of whatever size you ask for and pop it on the GPU and send it off to your model for you. Right? So a data loader is something that grabs individual items, combines them into a mini batch, pops them on the GPU for modeling. So that's called a data loader, and it comes from a data set. So you can see already there's kind of choices you have to make. You know, what kind of data set am I creating? What is the data for it? Where is it going to come from? And then when I create my data loader, what batch size do I want to use? Right? This still isn't enough to train a model. Not really, because we've got no way to validate the model. If all we have is a training set, then we have no way to know how we're doing because we need a separate set of held out data, a validation set, to see how we're getting along. So for that, we use a FastAI class called a data bunch. And a data bunch is something which, as it says here, binds together a training data loader and a valid data loader. And when you look at the FastAI docs, when you see these kind of monospace font things, they're always referring to some symbol you can look up elsewhere. So in this case, you can see trainDL is here. And there's no point knowing that there's an argument with a certain name unless you know what that argument is. So you should always look after the colon to find out that is a data loader. Okay, so when you create a data bunch, you're basically giving it a training set data loader and a validation set data loader. And that's now an object that you can send off to a learner and start learning, start fitting. Right? So they're the basic pieces. So coming back to here, this stuff, plus this line, is all the stuff which is creating the data set. So it's saying where did the images come from? Because the data set, the indexer returns two things. It returns the image and the labels, assuming it's an image data set. So where do the images come from? Where do the labels come from? And then I'm going to create two separate data sets, the training and the validation. This is the thing that actually turns them into PyTorch data sets. This is the thing that transforms them. Okay, and then this is actually going to create the data loader and the data bunch in one go. So let's look at some examples of this data block API, because once you understand the data block API, you'll never be lost for how to convert your data set into something you can start modeling with. So here's some examples of using the data block API. So for example, if you're looking at MNIST, which remember is the pictures and classes of handwritten numerals, you can do something like this. what kind of data set is this going to be? It's going to come from a list of image files which are in some folder, and they're labeled according to the folder name that they're in. And then we're going to split it into train and validation according to the folder that they're in, train and validation. You can optionally add a test set. We're going to be talking more about test sets later in the course. Okay, we'll convert those into PyTorch data sets now that that's all set up. We'll then transform them using this set of transforms. And we're going to transform into something of this size. And then we're going to convert them into a data bunch. So each of those stages inside these parentheses are various parameters you can pass to customize how that all works, right? But in the case of something like this MNIST data set, all the defaults pretty much work. So this is all fine. So here it is. So you can check, let's grab something